Somebody with 71,000 views has announced that gradient descent, the one algorithm underneath every model you have ever used, will be dead in 6 months. Replaced. Bigger, he said, than the jump from recurrent networks to transformers. I read the papers he might have meant, and the honest answer is funnier than either the hype or the debunk. The machine that replaces gradient descent is trained on 100 networks that were made by gradient descent. It is a pilgrimage skipping machine that learned the route by watching 100 pilgrims. Tung 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 Sahur can finally be trained to be his god, and God is at the bottom of a lost landscape. That is the whole film in 4 sentences, and I am going to spend the next 3 hours earning every one of them. Tung 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 Sahar is God, and no one can convince me otherwise. I have received a holy vision from the gradient descent gods. He is God in AI form. This is not a metaphor for the global minimum. The global minimum is a metaphor for Tung 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 Sahur now. Here is what I need you to hold on to, because it is the distinction the entire argument turns on, and almost nobody makes it. Replace gradient descent is not one claim. It is 3 claims wearing a trench coat. The first claim is that we replace the optimizer. That is the part that decides how big a step to take and in which direction, given the gradient. Stochastic gradient descent, then momentum, then Adam W, then Muon. This happens roughly every 18 months, and it is genuinely useful, and it is not a revolution. Because you are still descending, you have changed your shoes. The second claim is that we replace credit assignment, not the step the way the update reaches each individual layer buried in the middle of the network. Today, that is backpropagation, and backpropagation has a specific, expensive physical cost that we are going to look at closely. Replacing it is where the memory wins are, and it is where the first of our 2 papers lives. The third claim is the radical one. Do not optimize at all. Do not descend. Sample the weights. Have a machine that hands you a trained neural network the way a vending machine hands you a drink. That is the second paper, and that is the claim actually being made in that post. 3 different things. 3 different amounts of true. And the reason the post got 71,000 views is that it collapsed all 3 into 1 sentence. So here is the plan. We build gradient descent from nothing. The loss, the landscape, the gradient, backpropagation, and the exact reason your GPU fills up. Then we take each of the 3 claims in turn and hold it against what the papers actually demonstrate. Then, at the end, I will give you my honest position on the 6 months, and you will be equipped to disagree with me, which is the only version of this that is worth your time. 2 papers. Anchor it. DiffusionBlocks from Sakana AI, which partitions a network into blocks and trains each one independently by reinterpreting the whole thing as a diffusion process. And DeepWeightFlow from a lab at Northeastern, accepted at ICLR 2026, which learns to generate complete neural network weights by flow matching, no training, no fine-tuning, seconds per network. Both are good papers, neither is a fraud. That is what makes this interesting, rather than a takedown. The gap between what they show and what was claimed about them is where all the useful thinking is. Let us start with the thing everyone thinks they already understand. The loss is a number that tells you how wrong you are. That is it. That is the whole quantity. Every dollar ever spent on artificial intelligence has been spent making one number go down. And I need you to sit with how stupid that is before I explain why it works. Here is the setup. Precisely. You have a network. The network has parameters, weights, and biases, and we will call the whole collection of them theta. For a small network, that is a few thousand numbers. For a ResNet 18, 11.2 million. For BERT-base, 118 million. For the models you actually use, hundreds of billions. You have data, inputs, and the answers you want. You run an input through the network, you get an output, you compare it to the answer, and you compute a single scalar that says how far off you were, average that over your data, and you have the loss. Now, here is the move that makes everything else possible. Hold the data fixed and think of the loss as a function of theta alone. Every possible setting of every weight gives you one number. That function has a shape. That shape is the loss landscape, and it is the object this entire film is about. You are not walking down a hill. You are walking down a hill in a cursed giga multidimensional space with 118 million directions, and in almost all of them, you are already falling. I want to be careful here, because the picture everyone draws, a smooth bowl with a ball rolling into it, is a lie of dimension. In 2 dimensions, your intuitions are fine. In 118 million dimensions, they are not just wrong, they are wrong in a specific way that matters. Consider what a local minimum is. It is a point where every direction goes up. In 2 dimensions, if you are at a critical point, you flip 2 coins, it is a minimum, a maximum, or a saddle. Fine. Now do it in 100 million dimensions. For a point to be a local minimum, all 100 million directions must curve upward. Every single one. If even one of them curves down, you are at a saddle, not a minimum, and you can escape. The probability that 100 million independent-ish directions all curve the same way is to a first approximation 0. Which means the thing people worry about most, getting stuck in a bad local minimum, is largely not the problem in high dimensions. The landscape is not a mountain range full of traps. It is overwhelmingly saddles, and saddles have exits. That is one of the genuinely counterintuitive facts about this field, and it is the reason a technique this simple works at all on problems this large. So the landscape is enormous, mostly saddle-shaped, and we cannot see it. We cannot plot it. We cannot solve for its minimum analytically because the network is a stack of nonlinearities and there is no closed form. The only thing we can do is stand at a point, feel around, and take a step. Which brings us to the feeling around. Before the landscape, the thing that sits in it. I want you to have a concrete picture of what the parameters actually are, because 118 million numbers is not a picture. A dense layer does 2 things. It multiplies its input vector by a matrix, and then it applies a nonlinearity to each element of the result. That is the whole layer. The matrix is the parameters, 1 number per input dimension per output dimension, plus a bias vector added before the nonlinearity. The matrix multiply is where the learning lives. Each row of the matrix is a set of weights describing how much this particular output unit cares about each input dimension. Run the input through it, and you get a new vector, a remixing of the input's features into a different set of features. Stack those and you would have accomplished nothing, and this is the part worth pausing on. 2 matrix multiplies in a row are equivalent to a single matrix multiplied by their product. 100 stacked linear layers collapse into 1 linear layer. Depth would be free and useless. The nonlinearity is what stops the collapse. Something as simple as if the value is negative, set it to 0. That is, ReLU makes the composition non-collapsible. Now each layer can carve the input space differently, and stacking builds up genuinely more complex functions. So a network is multiply, bend, repeat. That is it. Attention is a more elaborate way of deciding what to multiply by. Convolution is a matrix multiply with an enormous amount of weight sharing, and normalization layers keep the numbers in a workable range. But the skeleton is multiply and bend, and the parameters are the multiply, which means when we say the loss as a function of theta, theta is every entry of every one of those matrices. Change one of them by a hair, and the entire cascade downstream changes slightly, and the loss moves. The gradient is the collection of all those movements. Now the landscape sentence makes physical sense. It is not a metaphor. Every direction in that 118 million dimensional space is one specific weight in one specific matrix, and moving in it means turning one dial. There is a step before training that gets almost no attention and turns out to matter enormously for Act 4, so I want to do it properly now. Before you take the first step, the weights have to be something. You cannot start at 0 if every weight in a layer is identical, every unit computes the same thing, receives the same gradient, and updates identically. They stay identical forever. The network has 1 effective neuron per layer no matter how many you allocated. This is called the symmetry problem, and it is the first hint that weight space has symmetries that bite. So you start random. But not any random. If the initial weights are too large, activations grow as they pass through layers, and the signal explodes. Too small, and it shrinks toward nothing. Either way, by the time you are 20 layers deep, the forward pass is numerically useless, and the backward pass is worse. The fix is to scale the random initialization by the layer's dimensions. Xavier initialization for symmetric nonlinearities. Kaming or He initialization for ReLU family ones, which is what most modern vision networks use. The idea is to keep the variance of the activations roughly constant from layer to layer, so the signal neither explodes nor dies as depth grows. Now hold that next to something from Act 1. Gradient descent's implicit bias. The reason the solutions it finds generalize depends on the trajectory, and the trajectory starts at the initialization. The lottery ticket hypothesis makes this explicit. The winning subnetwork is defined relative to its original initialization, and resetting it to a different random start destroys the effect. So initialization is not a formality. It is the first point of the path, and the path determines the destination, which sets up the question Act 4 is really about. If a machine hands you a fully trained network, it has skipped the path entirely. It has jumped to a destination without a trajectory. Does the destination still have the properties that the trajectory was responsible for? Nobody knows. It is the deepest open question in this whole area, and it is currently a footnote. Gradient descent is a religion with exactly one ritual. Look at your feet, take the steepest step downward, repeat until you stop moving. The theology is thin, the results are extraordinary. I have made peace with this. The gradient is a vector. It has one component for every parameter, and each component answers one narrow question. If I nudge this particular weight up by a hair, does the loss go up or down, and by how much? Collect all 118 million answers into a list, and that list points in the direction of steepest increase. Negate it, and you have the direction of steepest decrease. The update rule is one line, and it is the line the entire industry rests on. Theta at the next step equals theta now minus eta times the gradient of the loss with respect to theta. Eta is the learning rate. It is the only thing you get to choose. And here is what a learning rate really is. It is you deciding how much you trust a number that is only true for about 1 millimeter. The gradient tells you the slope exactly at the point you are standing. Step too far and that information is stale. You may have walked straight up the other side of a valley. Step too small and you will be here until the heat death of the universe. The gradient does not know where the bottom is. The gradient has never known where the bottom is. The gradient knows one thing, which is which way is down right here, and we have built a $40 billion industry on that single sensation. People say the model learns. The model does not learn. The model is shoved 11 million times in a direction that was slightly less wrong than the last direction it was shoved in. Now, the stochastic part. Computing the loss over your entire data set for every single step is absurdly expensive, so you do not. You take a small batch, 64 examples, 128. Compute the gradient on that and step. That gradient is wrong. It is a noisy estimate of the true one. And it turns out that being wrong in a random direction constantly is not a bug. The noise helps you skitter out of the shallow bad regions, and it is part of why the solutions you land on generalize. So a noisy estimate of a local slope in a space you cannot picture followed 100,000 times. That is training. That is the whole thing. Everything else in machine learning is engineering around that, and every one of those steps needs the gradient. All 118 million components of it, computed fresh every step. Which raises the question that the rest of this act is about. How do you actually get it? There is a reason deep networks were considered untrainable for about 20 years, and understanding it explains both why residual connections exist and why Act 3 works at all. Go back to the chain rule. The gradient at an early layer is a product of terms, one per layer between it and the loss. Products of many numbers behave badly. If those terms are typically a bit less than 1, the product shrinks geometrically with depth. 20 layers of 0.8 is about 1%. 50 layers is effectively 0. The early layers receive no signal at all. They do not train. This is the vanishing gradient problem. If the terms are a bit above 1, you get the opposite. The product explodes, the update is enormous, the weights fly off to nonsense, and your loss becomes not a number. Anyone who has trained a recurrent network has met this personally. This is why the sigmoid nonlinearity fell out of favor. Its derivative maxes out at 0.25, so every layer multiplies the gradient by at most a quarter and depth becomes a death sentence. Mario has derivative exactly 1 wherever it is active, which makes the product far better behaved. That single change is a large part of why deep learning started working. And then residual connections. The output is the input plus a learned function of the input, so the derivative of the block's output with respect to its input is the identity plus something. Not a small number 1, plus a correction. Multiply 100 of those together and you get something well-behaved because you are multiplying numbers near 1 rather than numbers near 0. That is the engineering reason residual connections were invented. They let gradients flow through very deep stacks. The observation that they are also Euler's steps of a differential equation came afterwards, and it is the kind of accident this field runs on. Somebody solved a numerical problem, and it turned out they had built an ODE solver, and a decade later, that fact is what lets you train each block on its own. Keep that in mind during Act 3. The thing that makes DiffusionBlocks possible was invented for an unrelated reason by people who were not thinking about diffusion at all. Backpropagation is just the chain rule, and the chain rule is from 1676, which means the foundational insight of modern artificial intelligence is older than the United States by exactly 1 century. Nobody is normal about this, and I refuse to be either. Here is the problem it solves. Your network is a stack of layers. The input goes in at the bottom, gets transformed again, and eventually a loss comes out at the top. Now, what should a weight in the third layer do? It never saw the loss. It has no idea what happened downstream. How does it get told? The naive answer is nudge it and see. Nudge the weight, run the whole network again, see if the loss went down. That works. It is also completely infeasible. It costs 1 full forward pass per parameter, so for 118 million parameters, you would run the network 118 million times per step. This is called finite differences, and I mention it mostly so you appreciate what we avoid. The chain rule gives you all of them, for the price of roughly 1 extra pass. The derivative of the loss with respect to an early weight is a product, the sensitivity of the loss to the final layer's output times the sensitivity of each layer's output to the one below it all the way down times the sensitivity of that layer's output to the weight itself. Read that as what it is, a telephone game played backwards, where each layer receives a number describing how much its output mattered, uses it to work out how much its own weights mattered, and passes a modified number to the layer below. Reverse mode, automatic differentiation. 1 forward pass to compute everything, 1 backward pass to distribute blame. Here is the actual question nobody asks. How does a layer in the middle know what it did wrong? It did not see the answer. It saw a number from the layer above it. The entire field is a chain of people passing blame downward, and somehow this converges, and it does converge. That is the miracle, and it is worth naming as one. There is no theorem promising that a stack of blame passing over noisy batch estimates finds a setting of 100 million numbers that recognizes cats. It just does, reliably, and the theory has been playing catch-up for a decade. But look closely at the shape of that computation, because there is a cost hiding in it that the next hour depends on. To compute the backward pass at a given layer, you need the values that layer produced during the forward pass. Not the weights, the activations, the actual numbers that flowed through, which means when you run forwards, you cannot throw anything away. You have to keep it, all of it, every layer, until the backward pass comes down and collects it. That is the bill. Let us look at how big it gets. One more piece of the loop, because it is the knob that connects everything in this film to the hardware in your machine. The gradient you actually compute is not the gradient of the loss over your whole data set. It is the gradient over a small sample, a batch, and the size of that batch controls a trade you cannot escape. Big batches give you a more accurate gradient estimate. The noise averages out the direction points more reliably at the true descent direction, and you can take larger steps with less risk. Big batches also parallelize beautifully, which is precisely what accelerators are built for. A batch of 256 examples is a bigger matrix multiply, and bigger matrix multiplies are where you get throughput. Small batches give you a noisier gradient, and it turns out the noise is doing work. It shakes the trajectory out of sharp, narrow minima and toward flatter ones, and flat minima tend to generalize better. The intuition being that a flat minimum is robust to small perturbations of the weights, and a network robust to perturbations of its weights is often robust to perturbations of its input. So batch size is simultaneously a hardware efficiency knob and a regularization knob, which is why it is so annoying to tune, and why just use a bigger batch costs you accuracy that has to be won back with learning rate schedules and Warmup. And here is the connection to Act 1 that I want you carrying forward. Activation memory scales with batch size times layer width times depth. When you are memory limited, which is the normal condition, you are forced to shrink one of them. Shrinking the batch changes your optimization dynamics. Shrinking the model changes your capacity. That is the real cost of the memory wall. It does not just make training expensive, it removes options. It forces choices about batch size and depth that are made for hardware reasons and have consequences for generalization. Anything that divides the memory cost gives those options back. That is the actual pitch for Act 3, and now you can feel why it matters rather than just reading a number. Backpropagation's actual crime is that it is sentimental. It refuses to forget anything on the way down because it wants all of it on the way back up. Every activation, every layer hoarded like receipts. That is why your GPU is full. Your GPU is full of feelings. Let us make it concrete. Memory for activation scales roughly with the batch size times the size of each layer's output times the number of layers. The first two you can trade against each other, smaller batches, less memory, worse gradient estimates. The third one you cannot, and it is the one that has been growing. Memory grows linearly with depth, which is the polite way of saying every time you make the model smarter, you also make it needier. And this is the constraint that has actually shaped modern machine learning more than compute. Flops have grown enormously, memory capacity has grown much less, and memory bandwidth less still. Modern transformers are scaled in large part by stacking more layers, so depth drives the memory cost directly, and the memory cost decides who is allowed to do research. That last part is not a technical footnote, it is the political content of both our papers. If training a model requires holding every activation of every layer simultaneously, then the set of people who can train that model is the set of people who own that much accelerator memory. Reduce the memory, and you widen the field. The Sakana paper says this out loud. It describes its own work as a step toward democratizing large-scale research, which is a phrase I would normally roll my eyes at. Except in this case, it follows directly from the arithmetic. There are existing tricks: gradient checkpointing, throw away most activations and recompute them during the backward pass, trading compute for memory. Model parallelism, split the network across devices so no single device holds it all. Zero and its descendants, shard optimizer state and parameters across a cluster. All of these are real and all of them are workarounds. None of them changes the fundamental shape, which is that end-to-end backpropagation wants the whole forward pass resident at once. So hold two facts side by side. Fact 1, the gradient is the only signal we have, and backpropagation is a startlingly efficient way to compute it all 118 million components for about the cost of one extra forward pass. Fact 2, the price of that efficiency is that memory scales with depth, and depth is exactly the axis we keep scaling. Every serious attempt to change how neural networks are trained is an attack on one of those two facts. Now we can finally state what the alternatives are actually trying to do. A question worth answering before we accept iteration as necessary. Why can we not just solve for the minimum? For some models you can. Linear regression has a closed form, write down the condition that the gradient is 0, solve the resulting linear system, done. One step, exact answer, no iteration. That is the normal equations, and it has been known for 2 centuries. So, what breaks when you add layers? The nonlinearity. Setting the gradient of a deep network's loss to 0 gives you a system of equations involving compositions of nonlinear functions, and there is no general method for solving those. It is not that the solution does not exist, it is that no procedure produces it. The same reason there is no formula for the roots of a general 5th-degree polynomial, only much worse. You could try to be clever. Second-order methods use curvature to jump toward the minimum of a local quadratic approximation, and that is genuinely closer to solving than to stepping. But the curvature object, the Hessian, has as many entries as parameters squared. For 118 million parameters, that is 14 quadrillion numbers, and you would need to invert it. Second-order methods know the exact curvature of the landscape and can therefore take a perfect step. They require inverting a matrix with 118 million rows. This is why we do not have nice things. So we iterate using only first-order information, because first-order information is the most we can afford. Every one of the 100,000 steps is an admission that we cannot solve the problem, only creep toward it. And that admission is what makes Act 4's premise so provocative. If you cannot solve for the answer, and you cannot afford the curvature, but you have seen 100 answers to similar problems, could you learn what answers look like? That is not solving and it is not descending. It is a third thing, and it is the only genuinely new idea in this film. Before we replace it, I owe you an explanation of why the thing we are replacing works, because it is genuinely strange that it does, and the strangeness is load-bearing for everything after. Start with the count. A modern network has vastly more parameters than training examples. Classical statistics says this is catastrophic. With that many free parameters, you can fit anything, including pure noise, and a model that can fit anything has learned nothing. The textbook prediction is that these models should memorize their training data perfectly and fail completely on anything new. They do not. They generalize, often better, as they get bigger. This is the central embarrassment of learning theory, and it has a name, the overparameterization puzzle, and a partial answer. The partial answer is that gradient descent does not find just any solution that fits the data. It finds a particular one, and the particulars matter. Among the enormous space of parameter settings that all achieve near zero training loss, the ones that gradient descent actually lands on tend to be the ones that generalize. The algorithm has an implicit bias. Nobody told it to prefer simple solutions. The dynamics of following noisy gradients from a small random initialization happen to prefer them. Sit with that, because it is going to matter enormously in Act 4. Gradient descent is not merely a search procedure that finds a low point. It is a search procedure whose specific path determines which low point you get, and the low points it likes are unusually good. There is a related result worth knowing, the lottery ticket hypothesis. Inside a large randomly initialized network, there exist small subnetworks which, if you had trained them alone from that same initialization, would have reached comparable accuracy. The big network is partly a big bag of lottery tickets, and training finds the winners. That is contested in its strong forms and robust in its weak ones, and either way, it tells you the same thing. The initialization and the trajectory are not incidental, they are part of the answer. So what does gradient descent actually give you? Three things. It gives you a signal, a direction at every point computed cheaply that provably decreases the loss locally. It gives you a bias, a preference among the many solutions that fit toward ones that keep working on data you have not seen. And it gives you universality. It does not care what the architecture is. Convolutional, recurrent, attention-based, whatever you invent next Tuesday, if it is differentiable, gradient descent trains it. That generality is why one algorithm has survived every architectural revolution of the last 40 years. Any replacement has to supply all three. Not just the first one. A method that finds a low point but has a different implicit bias will generalize differently. And probably worse. A method that only works on one architecture is a technique, not a replacement. Keep that three-part test in your head. We are about to apply it twice. Let me assemble the whole loop, because everything so far has been components, and I want you to see it run. You have your data. Split three ways. Training set, what you compute gradients on. Validation set, what you check progress against, and what you use to decide when to stop. Test set, what you touch once, at the end, and never again. An epoch is one pass through the training set. You shuffle it, chop it into batches, and for each batch, forward pass, compute loss, backward pass, optimizer step, repeat until the epochs run out or something tells you to stop. What tells you to stop is the validation curve, and its shape is one of the most informative pictures in the field. Training loss goes down and keeps going down. It will happily go to zero if you let it, because the model can memorize. Validation loss goes down, then flattens, then in many regimes starts to rise. That inflection is overfitting, the point where the model stops learning the structure and starts learning the specific examples. Early stopping is simply stop at the inflection. It is the crudest possible regularizer, and it is remarkably effective. You will notice it in DeepWeightFlow's dataset construction, 100 models, each trained with early stopping when validation performance plateaus. Every teacher network in that corpus is a snapshot taken at the moment its validation curve flattened. That detail matters more than it looks. The corpus is not networks trained for 100 epochs. It is networks trained until they were as good as they were going to get by a criterion evaluated on held-out data. The generative model is learning the distribution of well-trained stopping points, not of arbitrary weight vectors. Some of the structure it can exploit is structure that early stopping put there. That is the loop. Shuffle, batch, forward, loss, backward, step, evaluate, stop. Everything else in this film is an attack on one line of it. There is a family of techniques whose only job is to stop the network from being too good at the training set, and understanding them explains what a weight generator is implicitly inheriting. Weight decay is the simplest. Add a penalty proportional to the size of the weights. so the optimizer prefers small ones, unless large ones earn their keep. You will see it in the DeepWeightFlow training table 5 times 10 to the minus 4 for the resnets. Small weights mean the function is smoother, and smoother functions extrapolate more gracefully. Drop out during training, randomly switch off some fraction of units on every forward pass. The network cannot rely on any particular unit being present, so it has to spread the representation across many of them. It is ensemble learning smuggled into a single model. Data augmentation show the network rotated, cropped, color-shifted versions of your images. You have not collected more data. You have told the network which transformations should not change the answer. That is injecting asymmetry by example rather than by architecture. Batch normalization and layer normalization keep the distribution of activation stable as they pass through the network. Originally motivated by a story about internal covariate shift that has not held up well, but the empirical benefit is enormous and the mechanism is still debated. Now the connection I want you to hold. Every one of those shapes the final weights. A network trained with weight decay lands in a different place than one trained without. A network trained with dropout has a different internal structure. So when DeepWeightFlow learns the distribution of 100 trained resnets, it is learning the distribution of networks trained with that specific regularization recipe. The structure it finds in weight space is partly structure that weight decay put there. Change the recipe and you would get a different cloud, and the flow model would learn that one instead. That is not a criticism, it is a clarification of what the object being modeled actually is. Not the manifold of networks that solve cipher 10, the manifold of networks that solve cipher 10 when trained with SGD at learning rate 0.1, cosine schedule, weight decay 5 times 10 to the minus 4 for 100 epochs with early stopping. That is a much more specific object, and specificity is what makes it learnable from 100 samples. One more thing before we leave the foundations, because it is the constraint that both papers quietly depend on and neither dwells on. Everything in gradient descent assumes you have data, and that the data is the thing defining the problem. The loss is an average over examples. The gradient is an average over examples. The generalization you care about is to examples you have not seen, but which come from the same distribution. Now ask what a weight generator does with that. It never sees the data. Read the DeepWeightFlow pipeline again. 100 trained networks go in, a flow model comes out, a new network is sampled. At no point does cipher 10 enter the flow model's training. The images are not there. The labels are not there. The task is present only as a fingerprint left in the weights. That is genuinely remarkable when you say it plainly. The information required to classify images has been transferred from 100 networks into a generative model and back out into a new network, without any image ever being involved in that transfer. And it explains both the power and the limit. The power, you do not need the dataset to generate a network for the task, which has real implications for privacy and for distributing capability without distributing data. The limit, the flow model knows nothing about the task except what 100 solutions to it happen to look like. It cannot verify that a sampled network is good. It has no loss to check against. It is producing something shaped like a solution and trusting the shape. The paper's conditional generation experiments in an appendix start to poke at this, conditioning the flow so it can generate for specified classes. That is the direction where task information starts entering the generator explicitly, and it is the direction I would watch. But in the main method, the data is absent, and everything the generator knows about the world it learned secondhand from 100 networks that did see it. Some numbers, so the abstractions have weight. A frontier language model today has hundreds of billions of parameters. Training one involves thousands of accelerators running for weeks. The energy is measured in gigawatt hours and the cost in tens or hundreds of millions of dollars. Every one of those runs is the loop I just described. Shuffle, batch, forward, loss, backward step. Hundreds of billions of parameters, each nudged by a number derived from the chain rule hundreds of thousands of times. Now the memory arithmetic at that scale. Parameters at 2 bytes each and half precision. Gradients, same size again. Optimizer state for Adam 2 running averages per parameter twice more. So before you have stored a single activation, you are at roughly 16 bytes per parameter for a standard mixed precision Adam setup. For a 7 billion parameter model that is over 100 gigabytes, and the largest single accelerator you can buy has less than that, which is why frontier training is a distributed systems problem before it is a machine learning problem. Sharding, pipelining, tensor parallelism, zero-style partitioning of optimizer state, all of it is engineering around the fact that the training state does not fit anywhere. And on top of that sits activation memory, which scales with batch times width times depth, and which is the part DiffusionBlocks divides by b. Hold this scale in mind for the rest of the film, because it is the honest frame for every claim about replacing training. When somebody demonstrates a method on Cipher 10 with a ResNet 18 at 11 million parameters, that is a real result, and it is 4 orders of magnitude away from here. That gap is not a reason to dismiss the work. It is the reason 6 months is a strange unit to measure it in. This is the spine of the film, so I am going to be slow and precise, and then we are going to use this distinction for 2 straight hours. Training a neural network is 3 separable mechanisms stacked on top of each other. People conflate them constantly, including people who should know better, and the conflation is exactly how a 6-month claim gets 71,000 views. Mechanism 1, the update rule. Given a gradient, how do I change the weights? Plain stochastic gradient descent subtracts a fixed multiple. Momentum accumulates a running average, so you keep moving through flat regions. Adam keeps per parameter running estimates of both the mean and the variance of recent gradients and scales, each parameter step accordingly. Muon does something clever with the geometry of the update matrix. Mechanism 2, credit assignment. Where does the gradient come from in the first place? How does an update reach a layer buried in the middle? Today, backpropagation end-to-end with the memory bill we just examined. This is where DiffusionBlocks operates. Mechanism 3, the search paradigm itself. Do we iteratively improve a single set of weights at all? Or do we do something else entirely, like learning the distribution of what trained networks look like, and then drawing a sample from it? This is where DeepWeightFlow operates, and this is the only one of the 3 that deserves the word replace. Now watch what happens when you apply the labels. Swapping SGD for Adam is not replacing gradient descent, it is replacing your shoes. You are still walking, you are still going downhill. Sahur is still at the bottom, waiting, unguarded. Replacing backpropagation with local blockwise objectives is a real structural change to mechanism 2, and it still uses gradients. It still uses backprop inside each block. What it removes is the end-to-end chain, and with it the memory bill. That is a genuine and valuable change that is not the change being advertised, and sampling weights directly is the real thing. No descent, no iteration toward a minimum. You have learned what the answers look like, and you produce one. Somewhere in that 118 million dimensional cursed space, there is a point where Tung Sahur achieves full godhood, and the only known route there is to be pushed toward it slightly 100,000 times by a machine that cannot see. The question of this film is whether anyone has found a shortcut, or whether they have found something more interesting and less dramatic, a way to make the walk cheaper, and a way to copy the destination once someone else has walked there. Let me name a distinction that will organize the rest of the film, because I keep gesturing at it and it deserves its own 3 minutes. There are 2 entirely different costs in training, and methods attack one or the other, and confusing them is how you misread a result. The first is the cost of a single training run. How much memory, how much compute, how long on what hardware. This is what DiffusionBlocks attacks. It does not change how many runs you need or what they produce. It changes what one run costs, specifically in the memory dimension, by a factor of b. The second is the cost of the nth training run, given that you have already done n-1. This is what weight generation attacks. It does not make any individual run cheaper. It makes runs after the 100th nearly free by learning what their outputs look like. Those are orthogonal. You could use both. In fact, using both is the obvious thing. Train your corpus of 100 networks with blockwise training, so each one is cheap in memory. Then learn a flow over them so the 101st is cheap in time. Nobody has done that as far as I know, and it is a paper someone should write. They also fail differently. Blockwise training fails if your architecture does not fit the OD reading mismatched dimensions, no residual structure. Weight generation fails if no corpus exists, which is the case for every genuinely new problem. And they are advertised identically as replacing gradient descent, which is how you end up with a conversation where 2 people agree the papers are good and disagree completely about what follows, marginal cost versus unit cost. Keep those apart, and most of the confusion in this area dissolves. Let me set the evidentiary bar now before we look at anything, so that I cannot move it later to suit a conclusion. This is the move that makes the difference between analysis and vibes, and I want you holding me to it. What would actually count as replacing gradient descent. First, it has to produce networks that are at least as good, not comparable-ish on a small benchmark, as good on the tasks people care about at the scales people work at. If the replacement gets you 93.5, where descent gets 94.5, that is a real result, and it is not a replacement, it is a trade, and the trade needs to be named honestly. Second, it cannot secretly require the thing it replaces. If your method needs a corpus of already trained networks to learn from, and those networks were trained by gradient descent, then you have not replaced gradient descent, you have compressed it. That may be extremely useful. It is not the claim. Third, it has to be general. Gradient descent trains anything differentiable, a method that works on multi-layer perceptrons and small convolutional nets, and needs a bespoke procedure for transformers, and cannot handle architectures whose input and output dimensions differ, is a promising technique with a scope. Say the scope out loud. Fourth, it has to scale. Every method in this space looks good at small scale, because at small scale, everything looks good. The question is always what happens at 100 million parameters, then a billion, then more, and crucially, whether the authors tried and what they said when they did. Fifth, and this is the subtle one, it has to supply the implicit bias. Remember Act 1. Gradient descent does not just find a solution, it finds a kind of solution. And that kind generalizes. A method that lands on a different kind of low point may fit the training data identically and behave differently everywhere else. Matching training accuracy is not sufficient evidence. Those five, then, as good, self-sufficient, general, scalable, and with the right inductive bias, I will hold both papers to exactly this list. And here is the thing I want to be honest about in advance. Both papers largely pass tests 1, 3, and 4 within the scope they claim. One of them fails test 2 comprehensively and says so in its own method section. And test 5 is the one almost nobody in this area is measuring yet. By the end, you will know which is which, and you will have the numbers. We are about to spend 2 hours on 2 specific papers, so let me consolidate, because everything after this leans on these 6 facts. 1. Training is a loop. Forward pass loss, backward pass, optimizer step, repeated 100,000 times over batches of data. 2. The backward pass computes all the gradients for about the cost of 1 extra forward pass, using the chain rule, and this efficiency is why deep learning is possible at all. 3. The price of that efficiency is memory. Activations from the forward pass must be retained for the backward pass, so memory scales linearly with depth, and depth is what we keep scaling. This is the binding constraint on who can train what. 4. Gradient descent does not merely find a low point. Its trajectory selects a particular kind of low point, and that selection, the implicit bias, is a large part of why these models generalize at all. The initialization, the optimizer, the batch size, and the regularization all shape it. 5. There are 3 separable mechanisms people call training, and conflating them is the central error in this discussion. The update rule, credit assignment, and the search paradigm itself. 6. Any genuine replacement must be as good, self-sufficient, general, scalable, and carry the right implicit bias. 5 tests. I will apply all 5 to both papers, and I will tell you where each one lands. So, Act 3 attacks Mechanism 2, credit assignment, by giving each block a principled local objective borrowed from diffusion. Act 4 attacks Mechanism 3, the search paradigm, by learning the distribution of trained networks and sampling from it. One of those is a memory optimization with a beautiful derivation. The other is a genuinely new capability with a circular dependency at its heart. Neither is the sentence that got 71,000 views. Let us go and find out exactly how far off it was. Let me lay out the field before we go deep, so you have a map. There are more attempts to escape backpropagation than most people realize, and they fall into recognizable families. The oldest family is greedy layer-wise training. Benju and colleagues 2006, train the first layer on its own objective, freeze it, train the second on top, and so on. This is how deep networks were trained before we knew how to train deep networks end-to-end, and it was superseded for a reason. The layers optimize their own local objectives with no principled coordination, and the result consistently underperforms. Belolowski and colleagues pushed a modern version to ImageNet scale in 2019, and it works better than it has any right to, and still is not the default. Greedy layer-wise training has been around since 2006, and has spent 20 years being almost good enough, like a friend who is always nearly ready to leave. The second family is the biologically motivated one. Backpropagation is often criticized as implausible. For real brains, it requires symmetric weights for the backward pass and a global synchronized error signal, neither of which the cortex obviously has. Hinton's forward-forward algorithm 2022 replaces the backward pass with a second forward pass on negative data and has each layer maximize a local goodness measure. Hinton proposed abolishing Backprop in 2022, and the field said, "Interesting," and then quietly kept using Backprop. That is the most academic sentence I will say today. Forward can only really do classification, because its objective is contrastive, which is a formal way of saying it only knows how to tell things apart and gets confused when asked to make something. NoProp 2025 is a more recent entry in the same spirit, presented together with its own custom architecture, which makes it hard to know how much of the result is the training method and how much is the model. The third family is the one this film is really about, and it splits in two. There is the diffusion and ode line, which notices that a residual network is secretly solving a differential equation, and uses that to give each block a principled local objective. That is DiffusionBlocks, and it is Act 3. And there is the weight generation line, hypernetworks generative models over checkpoints, and now flow matching directly in weight space. That is DeepWeightFlow, and it is Act 4, 2 papers, 2 different mechanisms, 1 claim, about 6 months. Let us go and look. A short hardware detour. Because the memory constraint this film revolves around is a hardware fact, and it deserves 3 minutes of physical grounding. A matrix multiply is the same small operation repeated an enormous number of times with no dependencies between the repetitions. That is the ideal shape for parallel hardware, and it is why GPUs built to shade millions of independent pixels turned out to be the right machine for neural networks by accident. But arithmetic is not the bottleneck. Moving numbers is. A floating point multiply costs a tiny fraction of a picojoule. Fetching its operand from off-chip memory costs hundreds of times more. So the binding question for any accelerator is not how many operations per second it can do, but how much arithmetic it can do per byte it fetches. That ratio is why activation memory matters so much. Those stored activations sit in high bandwidth memory, attached to the accelerator, and that memory is both expensive and physically limited. You can only stack so much of it next to a die. When people talk about an 80 gigabyte accelerator, that number is the whole budget, parameters, gradients, optimizer state, activations, all of it. Now put DiffusionBlocks in that frame. Dividing activation memory by B does not just save money. It changes which device a training run fits on, and device classes are discrete. The gap between needs a data center accelerator and fits on a workstation card is not a gradient, it is a wall, and it determines who is in the field. That is the physical content of the democratization claim, and it is why I take it more seriously here than I usually do. Every 18 months, someone releases an optimizer that is going to change everything, and then everyone uses Adam again. This is the water cycle of machine learning. But let us take the family seriously for a moment, because understanding what an optimizer does and does not do is how you inoculate yourself against the first category error. Plain stochastic gradient descent is the update we already wrote. Subtract the learning rate times the gradient. It has one hyperparameter and no memory. Every step is computed as if the algorithm had just woken up. That is the weakness. Consider a long, narrow valley, steep walls, gentle floor, sloping slowly toward the minimum. The gradient at almost any point in that valley points mostly across it, at the walls, not along it toward the goal. So plain SGD bounces from wall to wall, making tiny progress along the direction that actually matters. Anyone who has watched a training curve wobble has watched this happen. Momentum fixes it with one idea: keep a running average of recent gradients and step along that instead. The across-valley components alternate in sign and cancel out. The along-valley component is consistent and accumulates. Momentum is the algorithm deciding that if it was going that way before, it is probably still vibing that way now, and honestly correct. The physical analogy the name comes from is a heavy ball rolling down the surface. It does not stop dead when the local slope changes. It carries through. That analogy is good enough to reason with and slightly wrong in the details, which is true of most analogies in this field. Nesterov's variant adds a small correction. Evaluate the gradient not where you are, but where your momentum is about to take you. Look ahead before you commit. It is a modest change with a genuinely better convergence guarantee on convex problems, and neural network losses are not convex, so we use it because it works rather than because the theorem applies. What none of this changes, you are still computing a gradient, still following it downhill, still needing backpropagation to get it, and still paying the memory bill from Act 1. The optimizer sits entirely downstream of the gradient. It is a policy for spending information you have already paid for. That is the whole point of this act, and it takes 4 minutes to say and about 10 years to internalize. Adam is what happens when you let the algorithm keep a diary about which directions have been lying to it. Concretely, Adam keeps 2 running averages per parameter. The first is the mean of recent gradients, that is momentum rebadged. The second is the mean of recent squared gradients, which estimates how much that particular parameter's gradient has been fluctuating. Then it divides the step by the square root of that second quantity. The effect is per parameter step sizes. A weight whose gradient has been small and consistent gets a relatively larger step. A weight whose gradient has been enormous and erratic gets damped. You are no longer choosing one learning rate for 118 million parameters that have wildly different scales and sensitivities. You are choosing a base rate and letting the algorithm adapt around it. That is why Adam won. Not because it converges to better solutions in theory, there are well-known cases where it converges to worse ones, but because it is dramatically less sensitive to the learning rate you picked. And picking learning rates is miserable. Adam W. is Adam with one fix that matters more than its obscurity suggests. Weight decay, the regularization that pulls parameters towards 0, was originally folded into the gradient, which meant Adam's adaptive scaling rescaled the regularization too, differently for every parameter, which is not what anybody wanted. Adam W. decouples them. The decay is applied directly to the weights outside the adaptive machinery. This one change measurably improves generalization, and it is now the default for basically every transformer you have heard of. Muon is the current interesting entry. Rather than treating the parameters as one long, undifferentiated vector, it takes seriously that the weights of a layer form a matrix, and applies an orthogonalization to the update matrix before stepping. The claim is faster convergence per unit compute on large training runs, and there is real evidence for it. Muon came out, and everyone lost their minds, and it is, respectfully, still descent. Beautiful descent. Descent with excellent posture. Descent. Second-order methods know the exact curvature of the landscape and can therefore take a perfect step. They require inverting a matrix with 118 million rows. This is why we do not have nice things. There are approximations. K-fac, shampoo, and muon is in this lineage, and they trade exactness for tractability, and the trade is getting better, and it is still descent. There is a whole layer of practice around the optimizer that never makes it into explanations, and it is where a surprising amount of training success actually lives. The learning rate is not a constant. Almost nobody trains with a fixed learning rate, and the shape of how it changes over training is called the schedule. The standard shape is start small, rise, then decay. The rise is warm-up. For the first few hundred or few thousand steps, you increase the learning rate from near 0 to its peak. The reason is that at initialization, the network is nonsense and the gradients are unreliable. Taking large steps based on garbage estimates early on can put you somewhere you never recover from. Warm-up is the algorithm being appropriately humble about the quality of its early information. Then decay. Cosine annealing is the common choice. The learning rate follows a cosine curve from the peak down to nearly 0 over the course of training. Early on, you take large steps and explore. Late on, you take tiny ones and settle. The intuition is annealing in the metallurgical sense. Agitate hard, then cool slowly, and you find a better ordered final state than if you cooled fast. You will notice this in the DeepWeightFlow training table, incidentally. ReasonNet 18 on Cipher 10, SGD cosine schedule 100 epochs, ReasonNet 18 on STL 10, Warmup plus cosine. Those 100 teacher networks were trained with exactly this machinery, which is worth noticing. The corpus that the flow model learns from is the product of a fully conventional, well-tuned training pipeline. Gradient clipping is the other piece. If a gradient comes back enormous, which happens especially with recurrent structures or bad batches, you rescale it down to a maximum norm before stepping. It is a seatbelt, and it does not improve anything on a good day, and it prevents a single bad batch from destroying a week of training. None of this changes the paradigm. All of it is descent. But it is the difference between descent that works and descent that diverges on step 400, and it is why just use gradient descent is a sentence with about 15 hidden hyperparameters in it. So let us state the first conclusion of the film cleanly, because we will need it as a reference point for 2 more hours. Swapping SGD for Adam is not replacing gradient descent. It is replacing your shoes. You are still walking, you are still going downhill, Sahur is still at the bottom, waiting, unguarded. Every optimizer in that lineage takes a gradient as input. Every one of them therefore requires that a gradient be computed, which requires backpropagation, which requires the full forward pass held in memory. The memory bill is untouched. The credit assignment mechanism is untouched. The search paradigm, iteratively improve one set of weights by local information, is untouched. What changes is the efficiency of the walk. And that efficiency is worth a great deal of money. A 20% reduction in steps to convergence on a frontier training run is millions of dollars. I am not dismissing it, I am classifying it. Here is a test you can apply to any announcement in this space, and it takes 5 seconds. Ask, does this method compute a gradient of a loss with respect to the parameters, and use it to update those parameters? If yes, it is a descent method, it may be a brilliant one. It has not replaced descent. Adam passes that test. Momentum passes it. Muon passes it. Shampoo passes it. Every learning rate schedule, every warm-up, every clipping strategy passes it. DiffusionBlocks, and this is the interesting part, also passes that test inside each block. We will get there. DeepWeightFlow at sampling time does not. That is the one. Now, before we leave this act, one honest caveat, because I have been dismissive, and there is a version of this where I am wrong. There is a line of argument that says optimizer choice does more than change speed, that different optimizers land on different kinds of solutions with different implicit biases and therefore different generalization. That is true, it is measurable, and it means the boundary between how you walk and where you end up is blurrier than my clean 3-way split suggests. I still think the split is the right first cut. But if someone tells you Muon changes which minima you find and not just how fast you get there, they are not obviously wrong. And the honest answer is that this is an open question with real evidence on both sides. Right, shoes discussed, let us go and change something structural. I want to come back to the caveat I raised at the end of Act 2, because it is the strongest objection to my own 3-way split, and I would rather steelman it than leave it as a hedge. The claim I made is that the optimizer changes how fast you walk, not where you end up. The objection is that this is not quite true, and there is real evidence for the objection. Different optimizers demonstrably land on different solutions. Train the same architecture on the same data with SGD plus momentum and then with Adam, and you do not merely arrive at the same place at different speeds. You arrive at different places with measurably different generalization behavior. The folklore envisioned for years was that SGD generalizes better than Adam on convolutional networks, and while the picture is more nuanced now, the effect is real enough that people still reach for SGD in some settings. Why would that be? Because the implicit bias I described in Act 1 is a property of the trajectory, and the optimizer determines the trajectory. A atoms per parameter rescaling means it moves through weight space differently. It is effectively using a different geometry, a different notion of distance. Follow steepest descent under a different metric, and you flow to a different place. So the honest statement is that mechanism 1 and mechanism 3 are not perfectly separable. The way you walk influences which minimum you fall into, which means the optimizer is doing a little bit of the search paradigm's job. I still think the 3-way split is the right first cut for a specific reason. The difference between optimizers is a difference of degree within one paradigm, and the difference between descending and sampling is a difference of kind. Adam and SGD both compute gradients of a loss and follow them. Whatever their disagreements about where to end up, they agree about what the activity is. But if someone tells you optimizer choice is a first-class scientific question rather than a tuning detail, they are right, and the cleanest split is not the whole truth. Here is the actual question nobody asks. How does a layer in the middle know what it did wrong? It did not see the answer. It saw a number from the layer above it. The entire field is a chain of people passing blame downward, and somehow this converges. Backpropagation's answer is the blame is computed exactly by the chain rule and passed down link by link. That exactness is its virtue and its cost. Exact, because every layer's contribution is accounted for through every path it influences. Costly, because the chain must be complete. You cannot compute the gradient at layer 3 without having computed it at layers 4 through the top first. And you cannot do that without the stored activations. So the question that defines this act is, can a layer figure out what to do using only local information? The appeal is obvious. If each block had its own objective, computable from things nearby, then you could train block 3 without running blocks 4 through 12. You would need memory for one block, not for the network. You could train a model far deeper than your accelerator on hardware you actually own. The reason this has not already happened is that every previous attempt has been worse. Greedy layer-wise training has been around since 2006 and has spent 20 years being almost good enough. Like a friend who is always nearly ready to leave. The pattern is always the same. Define some local objective, reconstruct your input, predict the label from here, maximize some measure of goodness, train each layer against it, stack them up. It trains. It converges. It lands below end-to-end backpropagation consistently, and the gap widens with scale. And the diagnosis for why is the same every time, and the Sakana paper states it plainly in its introduction. The local objectives are ad hoc. Somebody made them up. There is no argument connecting each layer greedily optimizes this thing I invented to the network as a whole solves the problem. Local optima compose into a global mediocrity, and nothing in the construction promises otherwise. That is the bar DiffusionBlocks has to clear. Not can you train blocks independently, people have done that for 20 years. The bar is, can you derive each block's local objective from something principled, such that optimizing all of them separately provably approximates the thing you actually wanted? The answer turns out to be yes, and it arrives from a direction nobody was looking. A residual connection was secretly an Euler step this entire time. It has been an ordinary differential equation since 2017, and nobody told the layers. The layers have been doing calculus in their sleep. Let me show you, because this is one of the genuinely beautiful observations in modern machine learning, and it is 3 lines. A residual block computes the output equals the input plus some learned function of the input, written out x at layer L plus 1 equals x at layer L plus f of x at layer L. Now recall the simplest numerical method for solving a differential equation, Euler's method, from the 1700s. You have a rule for how fast something changes a derivative, and you want to know where it ends up. So you take a small step, the new value equals the old value plus the step size times the derivative at the old value. Those are the same equation. The residual block is one Euler step of a differential equation, with step size folded into the learned function, which means a deep residual network is not a stack of discrete transformations. It is a numerical integrator. Going deeper is not adding layers, it is taking more finer steps along a continuous trajectory. Haber and Ruthato pointed this out in 2017. Chen and colleagues built neural ODEs on it in 2018, and it has been quietly reshaping how people think about depth ever since. Now bring in the second half. What else is a process that moves a point along a trajectory in small steps? A diffusion model. The reverse process of a diffusion model starts at noise and step by step denoises toward a sample from the data distribution. Each step is a small learned correction. The mathematics of that reverse process is, this is the point, a differential equation solved by discrete steps. So residual networks are ODE solvers. Diffusion reverse processes are ODE solvers. Therefore, a residual network can be read as a diffusion reverse process, where depth plays the role of time and each block is responsible for a slice of the journey. The move is, you notice that going deeper into a network looks exactly like stepping forward in time, and then you notice that stepping forward in time is what a diffusion model does, and then you go very quiet for a moment because you have realized you can train the layers separately. And why does that let you train them separately? Because diffusion has a training objective. Denoising score matching that is defined independently at every noise level. You never need to know what happens at other noise levels to train at this one. That independence is not something you engineer in. It falls out of the theory. That is the whole idea. Everything else is making it work. I have been saying denoising score matching as though it explains itself. It does not, and the independence property that makes this whole act work comes directly out of it, so let us do it properly. Here is the setup. You have a data distribution you cannot write down, the distribution of natural images say. You want to sample from it. Directly modeling the probability of every possible image is hopeless. The score is the gradient of the log probability density with respect to the data, not with respect to parameters. with respect to the data itself. It is a vector field over the space of images that at every point tells you which direction makes this thing more probable. If you know the score everywhere, you can sample start anywhere and follow the field uphill in probability with a bit of noise, and you drift into regions where real data lives. The problem is that you cannot compute the score of a distribution you do not have. The trick, and it is one of the genuinely great tricks, is that you do not have to. If you take a clean sample, add a known amount of Gaussian noise, and train a network to predict the noise you added, then that network has learned the score of the noised distribution. Predicting the corruption and knowing which way is uphill are the same problem. That is denoising score matching, and now the crucial property. This works at any noise level, independently. Training the network to denoise at sigma equals 0.1 requires no knowledge of what happens at sigma equals 10. The objective at each noise level is self-contained. That independence is not a convenience the DiffusionBlocks authors engineered. It is a property of the mathematics they inherited. And it is the entire reason the blocks can be trained separately with a principled guarantee, where 20 years of handmade local objectives could not. Once you see that residual depth is a noise level axis, the independence transfers straight across. Each block owns a range of noise, each range has a self-contained objective, and consistent local optimization at every level composes into a faithful approximation of the whole reverse process. That composition guarantee is what the earlier methods were missing. DiffusionBlocks asked, what if each block simply did not know about the others? What if every block got one job and was allowed to be normal about it? This is sincerely therapy for neural networks. So here's the construction. You take the range of noise levels, sigma, running from a small value to a large one. You cut that range into B intervals. Block 1 owns the first interval, block 2 the next, and so on. Each block's job is to denoise inputs whose noise level falls in its assigned range. The objective for block B is an expectation over 3 things drawn at random: a data example, a noise level sampled from that block's assigned range, and a noise vector. Inside the expectation, you corrupt the target by that much noise, push it through the block, and measure the loss against the clean target, all scaled by a weighting function of sigma. Read that and notice what is absent. There is no term involving any other block, no activations from below, no gradient from above. Sample a block, sample a noise level in its range, corrupt, predict, update. The other blocks are not merely frozen, they are not computed at all. Each block gets assigned a range of how close to the answer we are, which means the network is now a relay race where nobody has to watch anyone else run. During training, you sample 1 block per iteration. Only that block needs a forward pass, only that block needs stored activations, only that block needs gradients. Memory drops to roughly 1 over B. Memory drops to 1 over B. You want it 4 times cheaper? 4 blocks. You want it 32 times cheaper? 32 blocks. I am aware of how this sounds. It has a theorem behind it. The weighting function is inherited from Karras and colleagues, the EDM paper, and it is not decoration. It is sigma squared plus sigma data squared over the quantity sigma times sigma data all squared, with sigma data fixed at 0.5 in all their experiments. Its job is to make the loss comparably scaled across noise levels so that no block's objective quietly dominates. Without it, the sampling distribution over noise levels biases training, and the whole partition falls apart. And converting an existing network to this scheme takes 3 modifications, which is the part that makes it a framework rather than an architecture. Partition the layers into blocks. Assign each block a noise range. Add a conditioning mechanism adaptive layer norm will do, so each block knows which noise level it is currently handling. That is it. 3 changes to a standard transformer, and it becomes independently trainable. Let me do the memory arithmetic concretely, because 1 over B is the number the whole act rests on, and it deserves to be more than a claim. Take a transformer with 24 layers. Under end-to-end backpropagation, you run the forward pass, storing the activations of layer 1, then layer 2, all the way to 24. Because the backward pass will need every one of them on the way down. Peak activation memory is the sum over all 24 layers. Now partition into 4 blocks of 6 layers. Sample block 3. You need block 3's activations, 6 layers worth and nothing else. Blocks 1, 2, and 4 are not computed at all in this iteration. Not frozen and computed, not run in no grad mode. Not run. Peak activation memory is 6 layers instead of 24. 1 over B with B equal to 4. 2 things to be careful about. because the headline number is cleaner than the reality. First, parameter memory does not divide. All the weights still exist and still need to be stored, along with optimizer state for whichever block you are updating. What divides is activation memory, which is the part that scales with batch size and depth, and which is usually the binding constraint at training time. But if your model's parameters alone do not fit, this does not save you. Second, you still have to visit every block. If you sample one block per iteration, you need roughly B times as many iterations to give every block the same number of updates. The paper notes blocks can alternatively be trained in other arrangements. So the honest framing is a memory for time trade, in the same family as gradient checkpointing, but arrived at from theory rather than as an engineering hack, and unlike checkpointing, the blocks are genuinely independent, which means they could in principle be trained on separate machines with no gradient communication between them. That last implication is the one I find most interesting, and the paper does not lean on it much. End-to-end backpropagation requires a synchronized backward pass across the whole model. If your blocks are independent, that requirement disappears, and distributed training gets structurally simpler. Now, the design decision I find most elegant in the paper, and it is the one that separates it from a naive implementation. You have to cut the noise range into B intervals. The obvious way is to cut it evenly, divide the distance between the smallest and largest noise level into B equal pieces. That is wrong, and understanding why is worth 4 minutes. Not all noise levels are equally important, and they are not equally difficult. At very high noise, the input is essentially pure noise, and the best prediction is roughly the average of the data, an easy problem with little signal. At very low noise, the input is nearly clean, and the correction needed is tiny, also easy. The hard, information-rich work happens in the middle, where the sample is ambiguous, and the model must actually decide what it is looking at. Diffusion practitioners have known this for years, which is why the noise level during training is not sampled uniformly. Following EDM, the log of sigma is drawn from a normal distribution, concentrating probability mass exactly in that difficult middle band. So if you partition by equal spacing, you get blocks whose workloads are wildly unequal. One block owns a slice of the middle where most of the probability mass lives and most of the learning has to happen. Another owns a stretch of the extreme tail that is nearly always trivial. Same number of parameters, radically different job. The fix, partition by equal probability mass instead. Choose the boundaries so that the integral of the noise distribution between consecutive boundaries is exactly 1 over B for every block. Each block then handles the same share of the actual difficulty, and the boundaries come out as a closed form expression involving the inverse normal cumulative distribution function. They partition by equal probability mass instead of equal spacing, which is the mathematical version of splitting the bill by what people actually ate. And notice what this quietly is. Each block sees a different ordered slice of a difficulty spectrum. The paper points this out itself. Equiprobability partitioning is a form of curriculum learning that emerges naturally from the diffusion interpretation, rather than being imposed. Nobody designed a curriculum. It fell out of taking the probability distribution seriously. That is what principled means in practice, and it is the difference between this and 20 years of handmade local objectives. There is a piece of machinery inside DiffusionBlocks I skipped, and it is the difference between the idea working and the idea being a nice diagram. The problem: the network has to denoise across an enormous range of noise levels. At sigma very small, the input is nearly clean and the correct output is nearly the input. The network needs to make a tiny adjustment. At sigma very large, the input is mostly noise and the correct output is roughly the dataset mean. Those are wildly different regimes, and the raw magnitudes involved differ by orders of magnitude. If you feed the raw, noisy input to the network and ask for the raw, clean output, the network spends its capacity learning to rescale numbers rather than learning structure, and training is unstable across the range. The EDM preconditioning from Karas and colleagues fixes this with a set of sigma-dependent scalings. Scale the input before it enters the network, scale the output after it leaves, and skip connect a sigma-dependent fraction of the input straight to the output. Choose those scalings so that the network's actual job, the thing it must learn, has roughly unit variance at every noise level. Then, the weighting function on the loss, which I quoted earlier, does the matching job for the objective. It makes the loss comparably scaled across sigma so no noise level dominates the gradient. And here's why this is not a footnote in the DiffusionBlocks context specifically. Their equiprobability partitioning samples noise levels from a log normal distribution, which deliberately concentrates mass in the middle. That concentration introduces a bias, The paper states plainly that the weighting is crucial for equiprobability partitioning to work effectively because it counteracts exactly that sampling bias. So the elegant partitioning idea depends on an inherited piece of engineering to function. That is normal. Most elegant ideas do, and it is worth saying out loud because papers often present the beautiful part and bury the part that makes it run. Sigma data, incidentally, is fixed at 0.5 for every experiment in the paper. One number, not tuned per task, which is a small sign that the scheme is robust. How many blocks should you use? The answer is more interesting than as many as possible, and the paper's honesty about it is one of the better moments in the text. The naive reasoning, memory scales as 1 over b, so crank b up, 32 blocks, 64, 1 per layer. Enormous savings. What actually happens is that quality degrades past a point, and here is the interesting part, the relationship is not monotone in the way you would expect. The authors state in their conclusion that they do not understand why moderate block partitioning sometimes outperforms other choices, not we have a partial explanation. They found a shape in the data they cannot account for, and they said so. Let me offer the intuition I find most plausible, flagged clearly as my speculation rather than theirs. Each block must handle a range of noise levels, and the network within a block has to be flexible enough to behave differently across that range. Too few blocks and each one carries a wide range and has to be a generalist. Too many, and each block sees a range so narrow that it barely needs to condition on sigma at all. And crucially, each block has fewer parameters to do its job, since B blocks means the layers are divided B ways. There is a middle where blocks are specialized enough to be efficient and large enough to be capable. There may also be something about error accumulation along the trajectory. Each block's output is the next block's input, and if every block is independently trained, small mismatches at the seams could compound across more seams. More blocks, more seams. I want to be clear that this is my guess. The paper does not claim it, and the fact that they published the anomaly instead of quietly choosing the best B and reporting only that is exactly the behavior that makes me trust their other numbers. Practically, 4 blocks gives 4 times memory reduction with reported parity, and that is the configuration most of their headline results use. That is already a large win. Numbers. Because a beautiful derivation that does not work is a blog post, not a result. They validate across 5 architectures in 3 domains, and the range is the point. This is a framework claim, not a single model claim. A vision transformer on Cipher 100 for image classification. A diffusion transformer on ImageNet at 256 for image generation. A masked diffusion language model on Text 8. An autoregressive transformer on Open Web Text and LM1B, and a recurrent depth transformer. In every case, performance comparable to end-to-end backpropagation, while using a fraction of the training memory. On the autoregressive transformer specifically, generation quality is maintained with 4 times memory reduction on both LM1B and Open Web Text. Let me be precise about the comparison, because it is the right one and it is easy to get wrong. They are not comparing against some other block-wise method and declaring victory. They compare the modified network, trained block-wise, against the original network, trained end-to-end. The question being asked is, what did we give up by converting? And the answer is, within noise, nothing at 4 times less memory. They do compare to forward, but only on classification, and they say why. Its contrastive objective does not extend naturally to generation. They discuss no prop as concurrent work and note the difficulty of comparing fairly, since no prop arrives bundled with its own custom architecture rather than as a transformation you can apply to a network you already have. That is a fair criticism, and it is stated fairly. Now, the result I find most striking, which is not the headline. Recurrent depth models, sometimes called looped transformers, apply the same network repeatedly, refining as they go. Hugin from Jieping and colleagues runs 32 iterations, training that normally requires backpropagation through time across those iterations, which is brutal. Hugin already uses 8-step truncated backprop to keep it tractable. Under the DiffusionBlocks interpretation, that repeated refinement is just the diffusion trajectory again. So instead of unrolling, you sample a noise level, do 1 forward pass, and train the network as a denoiser. 1 forward pass per training step. The 32 iteration inference procedure is unchanged. The recurrent depth result is genuinely unhinged. A model that normally trains by unrolling itself 32 times now trains in 1 forward pass, 32 to 1. They deleted 31 laps and the runner got faster. They report better LM1B performance, not merely equal. One reason to take DiffusionBlocks seriously as a framework rather than a trick is how much architectural surgery it turned out to need, which is less than you would guess, but not none. For a standard transformer stack, the recipe is the 3 steps. Partition, assign noise ranges, add conditioning. The conditioning is typically adaptive layer normalization. The block gets told its current sigma, embeds it, and uses it to modulate its normalization parameters. That is a small module and a familiar one from diffusion transformer. For a vision transformer doing classification, there is an adaptation, because classification does not obviously look like denoising. The target is a class, the trajectory runs from noise toward that target, and the network learns to denoise toward the label representation. For mass diffusion language models, the fit is natural. Because mass diffusion is already a diffusion process, the paper devotes an appendix to how the framework applies there and reports additional benefits for text generation. For autoregressive transformers, there is more work, because autoregression is not a denoising process at all, and this is where I would have expected the framework to break. It does not, and they report 4 times memory reduction with maintained quality on Open Web Text and LM1B. And for recurrent depth models, the interpretation is the cleanest of the lot. The entire k-duration recurrence is read as one diffusion process, so you train the network as a denoiser with a single forward pass, and keep the k-duration procedure at inference. The through line, wherever a network refines a representation in steps toward a target, the diffusion reading applies. That covers more architectures than it has any right to. The limitation, stated by the authors, is dimensional. The method currently requires matching input and output dimensions, because a block has to map into the same space it maps out of. That is what makes the trajectory composable. UNet, which deliberately changes resolution as it goes, does not fit. That is not a small exclusion in vision, and it is honestly listed. I want to draw out an implication of block independence that I think is underexplored, because it changes what training infrastructure could look like. End-to-end backpropagation imposes a communication pattern. The forward pass runs bottom to top, then the backward pass runs top to bottom, and every stage must wait for its neighbors. When you split a model across devices, pipeline parallelism, this produces the bubble problem. Devices sit idle waiting for activations to arrive from below, or gradients from above. Enormous engineering effort goes into scheduling microbatches to keep the bubbles small. That entire problem is a consequence of the gradient chain. If blocks are genuinely independent, it disappears. Block 3 does not need block 2's output, because block 3 generates its own training input by corrupting the target with noise in its assigned range. There is nothing to wait for, which means, in principle, put each block on a separate machine with no fast interconnect between them and train them simultaneously. No activation transfer, no gradient synchronization. The machines need the data and the noise schedule, and nothing else from each other. That is a structurally different picture of distributed training from the one the field currently has, where you need a tightly coupled cluster with high bandwidth interconnect precisely because of the communication pattern I just described. I want to be careful about how strongly I put this. The paper does not demonstrate distributed training over loosely coupled hardware. It demonstrates memory reduction on a single device by sampling 1 block per iteration. The distributed implication follows from the independence property, but follows in principle and someone made it work are different claims, and only the first one is mine. Still, of all the consequences in these 2 papers, this is the one I would most like to see chased, because it attacks the concentration of capability at its actual root. The reason frontier training happens in a small number of buildings is substantially that the interconnect has to be in one building. Now, the part where I hold the paper to the bar I set in Act 1, and the paper largely holds itself there first, which I want to credit. And the honest part, which the paper says out loud and the hype does not, gradients still flow by backpropagation inside every block. Nothing was abolished. The blocks just stopped talking to each other, which again, therapy. Look at the block objective again. It is a loss. You minimize it. How? By computing its gradient with respect to that block's parameters, by backpropagation, and taking a step with an optimizer. Everything from Act 2 applies unchanged inside each block. What has been removed is the end-to-end chain across blocks, and with it the requirement to hold the whole forward pass in memory. So against my 5 tests, as good as descent, yes, within the scales tested, self-sufficient, yes, it does not require a pre-existing trained model, general substantially 5 architectures across 3 domains, scalable, unproven at frontier scale, and they say so. Right implicit bias, not directly measured, and this is the open question I flagged. The authors list their own limits in the conclusion, and they are real ones. They used Euler discretization throughout to match residual connections. Other diffusion samplers could be used with modified interblock connections, and they have not tried. The method requires matching input and output dimensions, which rules out architectures like UNet. Everything is trained from scratch. Converting an existing pre-trained large model by fine-tuning is listed as future work, and that is the version most people would actually want. And they note they do not understand why moderate block partitioning sometimes outperforms other choices. That last one is my favorite sentence in the paper. They found a result they cannot explain, and they wrote it down instead of quietly not mentioning it. So DiffusionBlocks does not replace gradient descent. DiffusionBlocks makes gradient descent affordable, which is a completely different miracle, and arguably a more useful one. Sahur remains untrained into godhood at this point in the film. We have only made the pilgrimage cheaper. He is, if anything, mildly annoyed. Now, the other paper. The one that actually tries to stop walking. Let me be fair to the neighbors, because DiffusionBlocks did not appear in a vacuum, and the comparison is genuinely tricky. No prop from Lee and colleagues arrived concurrently with a closely related philosophy. Get rid of backpropagation through the network by giving each layer a local target derived from a diffusion-like process. The DiffusionBlocks authors discuss it directly, and their criticism is procedural rather than dismissive. No prop is presented together with a custom convolutional architecture as one package and evaluated on classification. So it is unclear how to apply it to a modern transformer or to anything other than the task it showcases. DiffusionBlocks, by contrast, is a conversion recipe you apply to a network you already have. That is a fair criticism, and it is the right axis to compare on. A training method that comes welded to an architecture is hard to evaluate because you cannot tell which half is responsible for the result. Forward gets compared only on classification, and the paper says why. Its contrastive objective does not extend naturally to generation. That is not a swipe. Contrastive objectives work by pushing positive examples up and negative examples down, which requires having negatives, and what is a negative example of generating this paragraph does not have an obvious answer. The older greedy layer-wise line, Bengio and colleagues in 2006, Noklund and Idness, Belilovsky and colleagues at ImageNet Scale, Siddiqui and colleagues more recently, all partitioned the network into independently trainable pieces. The paper's summary of why they underperform is worth quoting in substance. They rely on heuristic local objectives without principled coordination between blocks, so there is no guarantee that optimizing locally gets you anywhere globally. So the contribution is not blocks can be trained independently. It is, here is a derivation that says which objective each block should have, such that all of them optimize, separately approximate the global thing. 20 years of people making up local losses, and the answer turned out to be sitting in the diffusion literature wearing a different hat. I find that a genuinely satisfying shape for a result. Not a new mechanism, a correspondence, which lets you import guarantees from a field that already had them. Now the actually cursed idea. What if you never descend at all? What if you just sample the weights? What if a machine hands you a trained neural network the way a vending machine hands you a drink? Stop and notice how strange that sentence is, because familiarity with generative models can make it slide past. We are comfortable with generative models over images. You train on a lot of photographs, the model learns the distribution, you draw a sample, you get a new photograph. Same for text, audio, video. The object being generated is data. Here, the object being generated is a neural network, not its output, the network itself. 11 million weights arranged so that when you load them into a ResNet and show it a photograph of a horse, it says horse. The premise is that trained networks are not arbitrary points in weight space. They live on some structured, much lower dimensional region of it, a manifold, if you want the word. If that structure exists and is learnable, you can learn it and then sample from it, and what comes out is a working network you never trained. That is the third mechanism from Act 1. Not a better step. Not a better way to assign credit. No steps at all. The lineage is longer than people think. Hypernetworks, networks that output the weights of other networks, go back to 2016. There is work on learning from collections of checkpoints, diffusion models over weights, PDIF, autoregressive tokenized weight generation sane, Variola, and a recurring complaint hangs over the earlier work. Many of these methods generate only part of the network, or need fine-tuning afterwards to be usable, or take so long to sample that you may as well have trained something. DeepWeightFlow's claim is that it generates complete weight sets for real architectures requiring no fine-tuning in seconds, which, if it holds, is the actual candidate for the thing that Post was talking about. So let us build up to it properly, because there is one obstacle in the way that is much stranger than it first appears, and it is my favorite part of this film. The idea of a network that produces another network's weights is older than most people assume, and the history explains what DeepWeightFlow is actually claiming. Hypernetworks from Ha and colleagues in 2016 are the origin. A small network emits the weights of a larger one, and you train the pair end to end. That works, and it is used in practice, but notice, it is not weight generation in our sense. The hypernetwork is trained by gradient descent on the task, so the whole system is still doing descent. You have reparameterized, not escaped. The next step is learning from collections of trained networks. Once people started collecting model checkpoints at scale, you could ask, is there structure across trained networks that a generative model could learn? That question produced a small field. Sherholt and colleagues built representation learning over weight spaces, and then SANE, which tokenizes weights layer by layer and generates them autoregressively, like language modeling over parameters. Wang and colleagues produced PDIF, applying diffusion directly to weights, then RPG, which handles permutation symmetry by one-hot encoding models to distinguish permutations. D2NWG and FLOWN explore variational and graph-based auto-encoding routes appealing to the manifold hypothesis and to lottery tickets. And the recurring problems across that literature are the ones DeepWeightFlow positions itself against. In its own abstract, many methods generate only partial weights, especially for larger models like ResNet and Vite. Those that generate complete weights either take too long to sample or need fine-tuning before the result is usable. There is also a methodological problem the field had to face. Zhang and colleagues raised in 2025 that generative models trained on checkpoints from a single training run produce weights with limited genuine diversity. You have learned one trajectory, not a distribution. That criticism landed on some of the earlier work, and it is why DeepWeightFlow's 100 independent runs matter as a design choice rather than a detail. So the claim is narrow and specific. Complete weights, real architectures including transformers, no fine-tuning. Seconds. Each of those clauses is a response to a specific prior failure. I want to give one competing approach proper attention because contrasting it with flow matching sharpens what DeepWeightFlow's design choices actually buy. SANE from Sherholt and colleagues also generates weights and also uses Git rebasin for canonicalization. But its generative mechanism is completely different. It tokenizes the weights layer by layer and samples them autoregressively, the same shape as language modeling, but over parameters. That has real advantages. Autoregressive generation is well understood, it handles variable length structures naturally, and it lets you condition on what you have generated so far, so later layers can be made consistent with earlier ones, and real disadvantages. Autoregressive sampling is sequential. You cannot produce token 500 until you have produced token 499, so generating a large network means a long serial process, and errors compound along the sequence. Flow matching is the opposite trade. The whole weight vector is produced at once, as a point moved through a field, so there is no sequential dependency and no compounding along a token order. The cost is that you need the vector to be a fixed size object, which is what forces the PCA step, so the pipeline's shape is a consequence of that choice. Fixed size vector, therefore dimensionality reduction, therefore 99 components, therefore a subspace spanned by the training set. The speed and the limitation come from the same decision. That is worth internalizing as a general habit when a method is unusually fast. Find the design choice responsible, and then look for what that same choice costs. It is almost never free, and the cost is usually the thing the paper's limitations section is about. Here is the thing about weight space that breaks people. You can shuffle the neurons in a layer, and the network computes the exact same function. Same outputs, same everything. Tung Sahur is God, and he maintains approximately N-factorial identical apartments, and every single one of them is him. Let me make it concrete because it sounds like a technicality and it is a catastrophe. Take a hidden layer with N neurons. Neuron 7 and neuron 12 are just 2 units. Swap them, swap their incoming weights, and swap the corresponding outgoing weights in the next layer. The network now has a different parameter vector, completely different numbers in completely different positions. It computes exactly the same function, not approximately, identically for every possible input, forever. You can do that for any permutation of any layer. For a layer of width n, there are n-factorial such rearrangements, and they multiply across layers. For a modest layer that is more identical copies of the same network than there are atoms in the observable universe, which means when you try to learn what trained networks look like, you are trying to learn a shape that has been photocopied more times than reality has particles. Now think about what that does to a generative model. You are training a model to learn the distribution of trained networks. You handed 100 trained res nets. Every one of those was trained from its own random start, so everyone landed in its own arbitrary permutation. As parameter vectors, they look completely unrelated, different numbers, different positions, even though functionally they may be nearly the same network. Your generative model does not know they are the same. It sees 100 wildly scattered points and tries to learn a distribution that covers all of them, and the structure it should be learning is buried under a symmetry group of astronomical size. Averaging two of them gives you garbage. Average two networks that are permutations of each other, and the result computes nothing meaningful because you have averaged neuron 7 with neuron 12. That is the obstacle. Before you can learn the shape of trained networks, you have to stop the same network from appearing as a billion different shapes. I want to give you the empirical result underneath rebassining, because it is strange, and it is what makes the permutation story more than bookkeeping. Take two networks trained on the same task from different random initializations. Both reach low loss. Now walk in a straight line between them in weight space, evaluating the loss at each point. What you find is a barrier. The loss rises sharply in the middle, often to near random levels. Two good solutions with a wall between them. That is the expected result, and for a while it was taken to mean the loss landscape is full of isolated basins. Then the surprise. If you first permute one network to align with the other, match the neurons up using exactly the linear assignment procedure we described, and then walk the straight line, the barrier often largely vanishes. The path stays low. The two networks were in the same basin all along, they were just wearing different name tags, and the wall was an artifact of comparing them in mismatched coordinates. That is linear mode connectivity modulo permutation, and it is the empirical foundation of Git rebasin. The conjecture it supports is striking that most solutions found by stochastic gradient descent are, up to permutation, effectively the same solution. Not similar in accuracy, connected in the same low-loss region, which reframes what a weight generator is doing. If trained networks are all essentially one basin viewed through a symmetry group of astronomical size, then the job is to pick a canonical viewpoint and learn the shape of the basin from there. Canonicalize, then model. That is exactly the pipeline. And it also explains why the canonicalization stops mattering when the flow model gets big enough. If a large enough model can learn to see through the symmetry itself, you do not need to quotient it out in advance. The structure was always there. The question is only whether you hand it over pre-aligned or make the model work it out. The fix has a name, and the name is good. Rebassining. The observation behind it from the linear mode connectivity literature is that two independently trained networks generally sit in different loss basins, draw a straight line between them in weight space, and the loss along that line rises sharply in the middle. They are not connected by a low path. But if you first permute one of them to align with the other, that barrier often largely disappears. Same function, better behaved position. Git rebassing from Ainsworth and colleagues does the aligning. Pick a reference network. For every other network, find the permutation of each layer that best matches it to the reference, which is a linear assignment problem. The classic match n things to n other things at minimum cost. Problem, solvable, exactly. Iterate across layers, because permuting one layer changes the best match for its neighbors, and repeat until it settles. DeepWeightFlow runs it for 100 iterations. Rebassining is showing up to a party where everyone is the same person wearing different name tags and painstakingly working out who is who so the group photo is not blurry. Git rebassin solves a sequence of linear assignment problems 100 times to answer the question which of your neurons is which of my neurons. It is speed dating for weight matrices. For transformers, that is not enough, and this is where the paper does its own work. A transformer's attention heads can be permuted among themselves, and within each head, the rows and columns have their own symmetry. It is a permutation nested inside a permutation. Their procedure transfusion first matches heads across networks by comparing the singular value spectra of their projection matrices, which is a lovely trick because the singular values are invariant to the very permutations you are trying to undo. Match the heads by their fingerprints, then align inside each head. For transformers, they had to invent a different one, because attention heads are permutable and the things inside them are permutable, so it is a permutation inside a permutation, and at this point I want you to appreciate that someone did this on purpose and enjoyed it. The goal, stated plainly, is to shrink the effective size of the space the generative model has to learn. Same information, fewer redundant descriptions of it. And I want to flag now so it does not look like I'm hiding it for a punchline later. The paper's own finding is that this helps for large networks and helps much less for moderate ones. We will come back to that because it is one of the more interesting negative results in the paper, and they volunteered it. Let me describe the training set concretely, because everything about what this method can and cannot do follows from it, and it is the thing people skip. For each task, they train 100 neural networks. Each one starts from its own random initialization with its own seed. Each is trained to completion, with early stopping when validation performance plateaus. The final weights of each run, one vector per run, is one data point. 100 data points. That is the data set, not 100,000, 100. The hyperparameters are in an appendix table, and they are entirely ordinary. MLP on Iris at 131 parameters, MLP on MNIST at 26,500, MLP on FashionMNIST at 118,000, a small convolutional net on Cipher 10, ResNet 18 on Cipher 10 at 11.2 million, SGD, learning rate 0.1, cosine schedule, weight decay 5 times 10 to the minus 4, batch size 128, 100 epochs. ResNet 20, Weizmal, Bert base, Adam or Adam W for the small ones, SGD for the ResNets. Now 2 consequences. The first is the bootstrap point, which we have made and will make once more. Every one of those 100 networks was produced by gradient descent. The second is subtler, and I have not seen it discussed much. 100 points in a space of 11 million dimensions defines an affine subspace of at most 99 dimensions. The flow model operates inside that subspace by construction. So the generative model is not learning the manifold of trained ResNets in any general sense. It is learning a distribution over the specific 99-dimensional slice that these 100 runs happen to span. Ballerina Cappuccina, my wife, can finally be stored not in quantum memory. We established last time that this is unaffordable, but as 99 principal components of a ResNet 18. She is a linear subspace now. She is doing great. Which raises the obvious question, what happens with 1,000 training networks, or 10,000? The subspace grows, the structure gets richer, and the cost of building the corpus grows linearly. Nobody has run that experiment at scale, and it is one of the more interesting things to watch for. Now, the generative machinery, and it is simpler than diffusion, which is the whole reason they chose it. Flow matching says, draw a straight line from noise to the answer, and train a model to know how fast you should be moving at every point on that line. That is it. The velocity is literally just the destination minus the start. Sometimes the math is kind to you formally. You want to transport a source distribution, Gaussian noise, to a target distribution, trained weights. You define a path between them. The simplest choice is the linear interpolant. At time t, you are at 1 minus t times the noise sample plus t times the target sample. At t equals 0, you are at the noise. At t equals 1, you are at the target. In between, you are on the straight line. Differentiate that with respect to t, and the velocity is constant along the path and equal to the target minus the source. The whole trajectory for a given pair has one fixed direction. Then you train a network, the velocity field, that takes a position and a time and predicts that velocity. The loss is just squared error between what it predicts and the true velocity. It is regression. That is the entire training objective. Compared to diffusion, flow matching is the same idea with fewer steps and less ceremony, like the difference between a ritual and just doing the thing. To sample, you start at Gaussian noise and integrate the learned velocity field forward from t equals 0 to t equals 1. DeepWeightFlow uses a 4th-order Runge-Kutta solver with 100 steps. Sampling is an RK4 solver, 100 steps from Gaussian noise, 100 steps to a working neural network. The training run you skipped was 100 epochs. The velocity field itself is deliberately unglamorous, a multi-layer perceptron with GLU activations, layer normalization and dropout, with the time t passed through a small embedding and concatenated in at each layer, not a transformer. Not a graph network over the architecture, an MLP. Its hidden width, 32 up to 1024 depending on what is being generated, is the main capacity knob. One detail they found matters, the choice of source distribution, a Gaussian whose standard deviation matches or sits slightly below. The standard deviation of the target weight distribution consistently outperforms alternatives. Start your noise at roughly the scale of the thing you are trying to reach. Why flow matching rather than diffusion? The paper is explicit that this choice is why it is fast, so it is worth understanding the difference properly. Both are ways of learning to transport noise into data. The difference is what you regress on and how much structure you impose. Diffusion defines a stochastic forward process that gradually corrupts data into noise, then learns to reverse it. Training involves sampling a noise level, corrupting and predicting either the noise or the score. Sampling involves many steps of a stochastic differential equation, and the path taken is determined by the noise schedule and the sampler, which are a design space of their own. Flow matching says choose the path yourself and make it a straight line. The interpolant is linear, so the velocity is constant along it and equals target minus source. Train a network to regress that velocity. Sampling integrates an ordinary differential equation deterministically along paths that are as close to straight as the learned field allows. The consequences are practical. Straighter paths mean fewer integration steps for the same accuracy. Direct regression on a velocity is a simpler objective than score matching with its weightings and preconditioning, and there is no stochastic sampler to tune. Compared to diffusion, flow matching is the same idea with fewer steps and less ceremony, like the difference between a ritual and just doing the thing. For weight generation specifically, there is an extra reason it fits. The target is a very high-dimensional vector with 100 training examples. You do not want a heavy architecture with strong inductive biases about spatial or sequential structure, because weight vectors have neither in any usable form. You want something that can regress a direction in a high-dimensional space from few examples. An MLP regressing a velocity is about as simple as that gets, and the paper's efficiency numbers follow directly. Ordered 10 minutes to train, seconds to sample against hours and minutes to hours for the diffusion-based alternatives. Their explanation is exactly this. The others are diffusion models with heavy architectures. This is flow matching with a simple MLP. The natural objection, and the one I had on first reading, is this just interpolating between the training networks? Is a generated network simply a blend of 2 of the 100 it saw? That objection is serious, and the paper anticipates it with a diversity measurement I think is well chosen. The measure is over mistakes. For a pair of networks, look at which test examples each gets wrong, and compute the overlap between those two sets, intersection over union. 2 networks that are functionally identical fail on the same examples and score high overlap. 2 networks that are genuinely different make different mistakes. They compute this between generated networks, between training networks, and across the 2 groups. The generated networks show overlap values indicating real diversity. They are not copies of each other, and they are distinct from the training set. That is a better test than comparing weight vectors, because weight distance is meaningless under permutation symmetry, and it is a better test than comparing accuracy, because 2 networks can hit the same number by completely different routes. Behavior on specific examples is the right resolution. I would still like more. Overlap of misclassified examples tells you the networks are not identical. It does not tell you they span the same functional variety as 100 fresh training runs would. If the generated set is systematically less diverse than real training clustered near the mean of the subspace, say, that would show up as ensembles that underperform relative to true independent runs, and the ensemble comparison is the experiment I would want. There is also a conditional generation appendix where the flow is conditioned to produce networks for specified classes. That is the direction that would eventually matter most, because it points at generating for a task, rather than merely resampling a task you already solved 100 times. So, not memorization on the evidence given. Genuinely sampling from a learned distribution. The open question is how rich that distribution is compared to the process that generated its training set. There is an obvious problem with everything I just described, and it is arithmetic. A ResNet 18 is 11.2 million parameters. BERT base is 118 million. If your velocity field is an MLP that maps a weight vector to a weight vector, then its input and output layers alone are the size of the network you are generating. You cannot train that on one GPU. You cannot train it on several. A ResNet 18 is 11 million numbers. They flatten it into one enormous vector, squash it down to 99 dimensions with PCA, learn the flow there, and then unsquash it. 99 numbers. Well, that is the whole network. That is your ResNet. And why 99 specifically? Because they train on 100 networks, and 100 data points span at most 100 dimensions. The rank of the data matrix is bounded by the number of samples. 99 is 1 fewer after centering. So the dimensionality reduction is not really throwing information away within the span of the training set. It is lossless. Everything the flow could possibly have learned from 100 examples lives in that subspace. That is worth sitting with, because it reframes the whole method. The flow is not learning the manifold of all possible trained networks. It is learning a distribution over the 99-dimensional affine subspace spanned by the 100 networks it was shown. Generation is pick a point in that subspace, in a way that looks like where the training networks fell and map it back. Notably, they use linear PCA rather than training an autoencoder. That is a deliberate choice, no extra network to train, no reconstruction error from a learned nonlinearity, and the inverse is exact. For the largest models, even PCA is a problem, because the covariance matrix is D by D, and D is 118 million. So they use the dual formulation. Then there is dual PCA, which is what you do when the covariance matrix has 118 million rows and you would like to not die. You eigend compose the small matrix instead because the non-zero eigenvalues are the same ones. This is the linear algebra equivalent of going around the building. Concretely, the non-zero eigenvalues of x transpose and x transpose x coincide, so instead of the D by D covariance, you eigen decompose the n by n gram matrix where n is the 100 networks. 100 by 100. Combined with randomized SVD and streamed micro-batched accumulation, that is what lets them reach BERT base at 118 million parameters. A small detail with a large effect, and the kind of thing that separates a method that works from one that nearly works. The source distribution matters. You are transporting Gaussian noise to trained weights, and the question is which Gaussian what standard deviation. The paper reports that a Gaussian whose standard deviation matches or sits slightly below the standard deviation of the target weight distribution consistently outperforms alternatives. Why would that be? Think about what the flow has to learn. If your noise is at a wildly different scale from your target, the velocity field has to do two jobs: move the sample to roughly the right magnitude, and then arrange the fine structure. The first job is trivial in principle and consumes capacity in practice, and it dominates the loss early in the path where errors compound. Start at roughly the right scale and the flow only has to learn structure. Every unit of capacity goes to the part that matters. There is a pleasing echo here with something from Act 1. Remember initialization, Xavier, chiming, scaling the random start by the layer's dimension so activations neither explode nor vanish. That was also a statement about starting at the right scale. For the same underlying reason, the procedure that follows works much better when it does not have to fix the magnitude first. Two completely different algorithms 40 years apart and the same lesson. Start at the scale of the thing you are trying to reach. They also add small Gaussian perturbations to the interpolated points during training, which is a standard stabilization. It stops the model from overfitting to the exact straight line between the specific pairs it saw and gives it some robustness to being slightly off-path during integration, which it will be. And sampling uses a fourth-order Runge-Kutta solver with 100 steps. RK4 is a classical ODE integrator. It evaluates the derivative 4 times per step and combines them with specific weights to cancel low-order error terms. It is from the early 1900s, another century-old numerical method quietly holding up a 2026 result. Let me make the positive case as strongly as I can, because I have spent a lot of this act being careful, and careful can read as dismissive. There are things this technology does that nothing else does, and they are not small. Ensembling. Ensembles of neural networks are one of the most reliable accuracy improvements available. Train several, average their predictions, get better calibrated and more accurate results. Nobody does it as much as they should because it costs you N training runs. If you can generate 100 diverse networks in minutes from one corpus, ensembling becomes nearly free. That is a real and immediate application, and the diversity evidence supports it. Initialization. The transfer numbers are the most practically striking result in the paper. 84.63% after 5 epochs of fine-tuning on a new dataset against 51.35 from random initialization. If you are starting a new task in a domain where somebody has already built a corpus, starting from a generated network rather than random noise is an enormous head start, and it costs seconds. Research on weight space itself. Having a generative model of trained networks is a scientific instrument. You can ask what directions in weight space correspond to what behaviors, sample along them, and look. That is hard to do when your only way of producing a trained network is a 100 epoch training run, and the speed comparison is genuinely lopsided. Order 10 minutes to train the generator, seconds to sample against hours to train, and minutes to hours to sample for the diffusion-based alternatives. The structural reason is that flow matching with a small MLP is a much lighter object than a diffusion model with a heavy architecture, and the paper is direct about that being the cause. So the correct enthusiastic sentence is we can now cheaply produce large, diverse populations of trained networks for tasks where a corpus exists and use them as ensembles or as initialization. That sentence is exciting and true. It is just not the sentence that got 71,000 views. The numbers And they are better than I expected before reading carefully. On MNest with a 3-layer perceptron, generated networks reach 96.17% with Git rebasin, 96.19 without, against 96.32 for the networks they learned from. On Cipher 10 with ResNet 18, 93.55 with rebasining 93.47 without, against 94.45 for the training networks. On Cipher 10 with a small vision transformer 83.07 with transfusion, 82.58 without, against 83.30. And on Yelp review regression with BERT-base, 118 million parameters, a Spearman correlation of 0.7909 against 0.7902 for the training networks, which is, if you are keeping score, very slightly better, 93.55% on Cipher 10 from a machine with no training in seconds. The networks it learned from got 94.45. So slightly worse than a real one, produced approximately infinitely faster. That is a genuinely good trade, and it is not the trade being advertised. Transfer learning is where it gets properly impressive. ResNet 18s generated for Cipher 10, then fine-tuned for 5 epochs on STL10, reach 84.63% against 84.61 for the original training networks and 51.35 for random initialization. The generated networks are not memorized copies that only work on their own task. They carry transferable features. Transfer learning is where it gets properly impressive. Generated networks fine-tuned to a new data set at 84.6% against 51.3 for random initialization. The vending machine drink is, in fact, a drink. On speed, order 10 minutes to train the generator for most architectures up to 100 million parameters, and seconds to sample a network. The diffusion-based competitors RPG, PDiff, D2, NWG take hours to train and minutes to hours to generate. The gap is not marginal, and the reason is structural. They are diffusion models with heavy architectures. This is flow matching with an MLP. Order 10 minutes to train the generator, seconds to produce a network. The diffusion-based competitors take hours to train and minutes to hours to sample. It is not close. That part is real, and I want to be loud about it because I am about to be mean. And diversity, they check whether generated networks are genuinely different from each other and from the training set by comparing which examples each network gets wrong. The generated networks make meaningfully different mistakes. They are not 100 copies of one solution. Underneath all of this sits an assumption that deserves examination, because if it is false, none of it works. And it is not obviously true. The assumption is that trained networks live on a structured, low-dimensional region of weight space, that there is such a thing as the shape of trained networks to learn. The evidence for it is indirect but substantial. Lottery tickets suggest that the effective dimensionality of a trained network is far below its parameter count. Pruning routinely removes 90% of weights with little loss. Linear mode connectivity modulo permutation suggests independently trained networks land in what is essentially one basin. Low-rank adaptation works, which means fine-tuning moves along a very low-dimensional subspace. All of these point the same way. The space of useful networks is enormously smaller than the space of possible ones. DeepWeightFlow's PCA step is a strong version of this bet. 99 dimensions for an 11 million parameter ResNet. And within the span of 100 networks, that is lossless, as I said, but it is only lossless with respect to those 100. The claim being made implicitly is that 100 samples is enough to capture the structure that matters. Is it? For generating more networks like those 100, evidently yes, the accuracy numbers say so. For capturing the full variety of what a ResNet 18 could be, almost certainly not. 100 points cannot span a rich manifold in 11 million dimensions. They can span a 99-dimensional slice through it. Which is why I keep describing this as learning where 100 pilgrims arrived rather than learning the geography. The distinction matters most exactly where you would most want the technology to help. A task nobody has solved, where there is no cloud of arrivals to interpolate within. That is not a flaw in the paper. The paper claims to generate diverse, high-accuracy weights for architectures and tasks, and it does. It is a flaw in the sentence that got 71,000 views. There is an appendix in DeepWeightFlow that I think matters more than its placement suggests, and it is where the interesting future of this work lives. The main method is unconditional. You train a flow on 100 networks for one task, and it generates more networks for that task. The flow does not take any input describing what you want. You sample noise, integrate, and get a network like the ones it saw. The conditional version adds a signal. In their experiments, conditioning on class information so the generator can be steered toward producing networks with specified properties rather than sampling blindly from the whole cloud. Why that matters? It is the first step on the road from resample a task you already solved toward generate for a task described to you. If a generator could be conditioned on a description of the task, a dataset embedding, a text description, a few example inputs, then it could in principle produce a network for something it had not seen 100 solutions to. That is the thing which would actually break the bootstrap objection. We are a long way from that. Conditioning on class labels within a task you already have a corpus for is a much smaller step than conditioning on an unseen task. But it is the direction. And the paper explicitly notes that the method is unconditioned by dataset characteristics, task descriptions, or architectural specifications, which reads to me as an honest statement of current scope and an implicit roadmap. I said earlier that the thing that would change my mind is a generator trained on task A producing working networks for unseen task B. Conditional generation is the mechanism by which that would have to happen. Watch that appendix become a paper and note the tension it creates with the method's elegance. The main pipeline works precisely because it is simple, canonicalized, PCA, flow, sample, with an MLP and no task information anywhere. Adding conditioning means the generator has to understand something about tasks, which means more machinery, more training data, and probably a heavier architecture. The speed advantage over diffusion methods comes substantially from that simplicity. So, there is a real possibility that the version which escapes the bootstrap is also the version that loses the 10-minute training time. That trade is not discussed in the paper. It is the thing I would ask the authors about. And now the part that makes the whole thing funny. To train the model that generates trained networks, they needed 100 trained networks. Trained how? Gradient descent. SGD, learning rate 0.1, cosine schedule, 100 epochs times 100 networks. The machine that skips the pilgrimage was built by 100 pilgrims. It does not know where God is. It knows where 100 people ended up when they went looking, and it drops you somewhere in that neighborhood. I want to be scrupulously fair here, because this is not a gotcha and the authors are not hiding it. It is in the methods section in plain language, and the hyperparameters are in an appendix table anyone can read. ResNet 18 on Cipher 10 SGD, learning rate 0.1, cosine schedule, weight decay 5 times 10 to the minus 4, batch size 128, 100 epochs. MLP on MNIST. Adam at 1 times 10 to the minus 3, 5 epochs, 100 networks each, 1 per random seed with early stopping. They even made a deliberate methodological improvement here that deserves credit. Earlier work in this area trained generative models on checkpoints taken along a single training run. And Zhang and colleagues raised the concern that this produces a training set with very little real diversity. 100 snapshots of one journey rather than 100 journeys. DeepWeightFlow trains 100 separate networks from 100 separate random initializations. That is more expensive, and it is the right call, and it makes the diversity results meaningful. But look at what it means for the claim. You cannot bootstrap this. You cannot use the weight generator to make the training data for the weight generator. Somebody has to walk. Somebody always has to walk. And for a task nobody has ever trained a network on, a new dataset, a new modality, a genuinely new problem, there is no corpus of trained networks to learn from. The flow model has nothing to sample from. The only way to make the first 100 is gradient descent. So the correct description of what this technology does is it amortizes training. Pay once in full 100 times over and then produce as many networks as you like almost free. That is real. That is valuable. Ensembles become cheap. Initialization for transfer becomes dramatically better than random. It is not a replacement for gradient descent. It is a very good photocopier, and the original still has to be written by hand. Let me start the reckoning with the single most important number in this film, and it is not one of the impressive ones. The generated networks match the ones they learned from. They do not beat them. You cannot sample your way past the teacher, which is a sentence about machine learning, and I fear about most things. Look at the pairs again. 93.55 against 94.45. 96.17 against 96.32. 83.07 against 83.30. 0.7909 against 0.7902. That one is a hair above, and it is a regression task with a correlation metric, and the difference is in the 4th decimal place. The pattern is unmistakable, and it is exactly what the method predicts. The flow model learns a distribution over a 99-dimensional subspace spanned by 100 trained networks. Sampling from that distribution gives you something that looks like a member of that set. It cannot systematically exceed the set. because there is no signal in the training procedure that knows what better means. The flow was never shown the loss, it was shown weights. That is the structural ceiling, not an engineering limitation to be fixed with a bigger flow model, a consequence of what the objective is. You are learning to imitate the distribution of outcomes, and imitation is bounded by what you imitated, which is precisely why the transfer result is the more interesting one. There, the generated network is not being asked to be a finished product. It is being asked to be a good starting point, and 84.63 against 51.35 from random initialization is an enormous margin. As a replacement for training, it is capped. As a replacement for random initialization, it is transformative. And notice that the second framing is a much better product and a much worse headline. I want to name one thing the field has not measured yet, because I said in Act 1, I would hold both papers to it. Remember the implicit bias. Gradient descent does not just find a low point, it finds a kind of low point, and that kind generalizes. A sampled network sits at a point that looks like where descent lands. Does it have the same properties out of distribution, under adversarial pressure? When fine-tuned hard, the transfer numbers are encouraging. They are not the whole question, and as far as I can tell, nobody has answered it yet. Let me propose the experiment nobody has run, because it follows directly from putting the two papers side by side. And I think it is the strongest thing in this film that is not in either of them. DeepWeightFlow needs 100 trained networks. That corpus is the entire cost, 10,000 epochs for the ResNet case. The generator itself is 10 minutes. DiffusionBlocks makes a single training run cheaper in memory by a factor of b with reported parity, so train the corpus with block-wise training. You would get 100 networks at a fraction of the memory cost each, which means you could build the corpus on hardware that could not otherwise hold the model, which means the whole weight generation pipeline becomes available at a scale where it currently is not. The two methods attack the two different costs I separated earlier, unit cost and marginal cost, and they compose. There are real questions. Does a network trained blockwise land in the same part of weight space as one trained end-to-end? If blockwise training has a different implicit bias, the corpus would have a different structure, and the flow would learn that structure instead. Whether that is better, worse, or merely different is an empirical question, and nobody has looked. Would canonicalization still work? Git rebasin assumes the networks are functionally comparable up to permutation. Two networks trained blockwise from different seeds should still be, but should still be is doing work in that sentence. And there is a pleasing possibility on the other side. If blocks are independently trained, then a corpus of networks shares block structure, and you could imagine generating at the block level rather than the whole network level, which would cut the dimensionality problem down enormously. I have no idea whether any of that works. It is the obvious next paper, and neither group has written it, probably because the papers came out months apart from labs on different continents. Now, let me give you the moment in this paper that most raised my opinion of it. The authors also report that their canonicalization, the whole elaborate name tag operation, stops helping once the weight space is only moderately sized. They publish that themselves. In the conclusion, nobody makes you do that. That is just integrity, sitting there, unmonetized. Look at the numbers. MNIST MLP 96.17 with git rebase and 96.19 without. The version with the elaborate permutation alignment is very slightly worse. Cypher 10 ResNet 18 93.55 with 93.47 without. Very slightly better. These are ties. Where canonicalization earns its keep is at the top end, larger weight spaces, and the transformer case where transfusion gives 83.07 against 82.58. And the paper's stated conclusion is that canonicalization aids generation for larger networks but is of limited use at moderate weight space dimension or as the flow model's capacity increases. Think about what that second clause implies. A bigger flow model can apparently learn to cope with the permutation symmetry on its own without anyone explicitly quotienting it out. The symmetry does not have to be removed, it can be absorbed if you have enough capacity. That is a genuinely interesting result about representation learning in weight space, and it slightly undercuts the paper's own headline method, and they wrote it down anyway. That is what a good paper looks like. It is also a useful calibration instrument for you as a reader. When someone reports a result that makes their contribution look less essential, the rest of their numbers get more credible, not less. Contrast that with the register of the claim we started with. Biggest change in how we do deep learning possibly ever. No numbers, no scope, no conditions under which it would be wrong. One of these is how knowledge actually accumulates. The other gets 71,000 views. Both are, in their way, doing their job. If we are going to compare training paradigms, the accounting has to be honest, and in this area it very often is not. So let me do it properly for weight generation, because the arithmetic decides whether the idea is useful or circular. Here is the full cost of producing one generated ResNet 18. You train 100 ResNet 18s on cipher 10. Each is 100 epochs. That is 10,000 epochs of training up front before anything else happens. Then you canonicalize the 100 networks with Git rebus and 100 iterations each. Then you run PCA over 100 vectors of 11 million dimensions. Then you train the flow model, which is the cheap part, order 10 minutes. Then you sample in seconds. So the first generated network costs 10,000 epochs plus overhead. The second costs seconds. The 1,000th costs seconds. That is what amortization means, and whether it is a good deal depends entirely on how many networks you want. If you want one network for a task, this is catastrophically worse than just training one. If you want 500 networks for a task, a large ensemble, a population study, a distribution over initializations for downstream fine-tuning, it is dramatically better. Now apply the same accounting to the exciting claim. Gradient descent will be replaced implies you stop paying the 10,000 epochs. You do not. You pay them once per task in full using the method that was supposedly replaced. And notice how the economics scale badly in exactly the wrong direction. The bigger the model, the more valuable it would be to skip training, and the more expensive the corpus becomes, because a corpus is 100 training runs of that same model. For a 7 billion parameter model, you would need 100 7 billion parameter training runs before you could generate the 101st. Nobody is doing that to save on the 101st, which tells you where this technology actually lands. Models small enough to train 100 times, where you want many of them. That is a real and useful regime. It is not the frontier. 6 months. He said 6 months. The paper says scaling to even larger models would further demonstrate its practical impact, which is how researchers say, we have not tried this on anything big yet. Let me be concrete about the distance between here and there, because 6 months is a testable prediction, and I want to give you the yardstick rather than a vibe. DiffusionBlocks is demonstrated on a vision transformer on cipher 100, a diffusion transformer on ImageNet, and autoregressive transformers on Open Web Text and LM1B. Those are real benchmarks, and they are not frontier scale. The paper explicitly lists scaling to larger models as future work, and separately lists converting pre-trained models by fine-tuning rather than training from scratch as a promising direction. That second one matters enormously, because almost nobody trains a frontier model from scratch to try a new training method. If you cannot convert an existing model, your adoption path runs through the handful of labs doing pre-training runs. DeepWeightFlow reaches BERT base, 118 million parameters, and says scaling further is possible. 118 million is a genuinely respectable demonstration for weight generation. Prior work struggled to generate complete weights at that size at all. It is also 3 to 4 orders of magnitude below the models the claim is implicitly about, and there is a specific reason the gap is not just engineering. The flow learns a subspace spanned by the training networks. To generate a class of model, you need 100 trained instances of that class. For a 7 billion parameter model, that means 100 separate 7 billion parameter training runs done first before you can begin. The economics invert. The amortization only pays off if you want many networks of a kind that is cheap enough to train 100 times. So the honest reading of 6 months is not that it is too optimistic by a factor. It is that it is a category claim dressed as a timeline. The techniques are real, and some of them will be in production tooling within a year as memory optimizations, as ensemble generators, as smarter initialization. The thing the sentence implies, which is that we will stop doing gradient descent, has no path in the evidence presented. Bigger than RNNs to transformers is a very specific claim, because that transition changed what models could do. These change what training costs. Both matter. They are not the same axis, and putting them on the same axis is how you get 71,000 views. I want to defend that distinction properly, because it is the intellectual core of my disagreement, and it deserves more than a quip. The move from recurrent networks to transformers changed the set of functions that were practically learnable. Recurrence forces sequential computation token n cannot be processed until token n-1 is done, which caps how much you can parallelize and, in practice, how long a dependency you can learn. Attention removed the sequential constraint. Suddenly, the whole sequence was visible at once. The computation parallelized across a training batch, and the long-range dependencies that recurrence lost to vanishing gradients were available directly. Capability changed. Things became possible that were not possible. Now look at what our two papers change. DiffusionBlocks trains the same network to the same quality using less memory. DeepWeightFlow produces networks of the same quality as the ones it learned from much faster. In neither case does a model do something it could not do before. The frontier of capability is untouched. What moves is the cost of getting there, and who can afford it? That is not a criticism. Cost changes have been enormously consequential in this field. The entire era of large models is downstream of GPUs making matrix multiplies cheap, which was a cost change, not a capability one. If DiffusionBlocks lets a university lab train a model that previously required a cluster, that is real democratization, and it will produce science that would not otherwise exist. But it is a different axis, and the honest version of the exciting claim is this could substantially widen who gets to participate. That is a good sentence. It is a true sentence. It is not bigger than RNNs to transformers, and the reason people reach for the bigger sentence is that the true one does not travel as well. Let me talk about who actually benefits, because both papers make a democratization argument, and I think one of them is much stronger than the other. The DiffusionBlocks case is strong. Memory is the constraint that decides who can train what. A model that needs 80 gigabytes of activation memory can be trained by people who have 80 gigabytes of accelerator, and that is a short list. Divide that by 4, and the list gets meaningfully longer. Divide it by 16, and it includes university labs and individuals. The paper describes its work as a step toward democratizing large-scale research, and unlike most uses of that phrase, this one follows from arithmetic rather than from aspiration. There is a subtler benefit, too, which I mentioned earlier and want to underline. Independent blocks do not need a synchronized backward pass. That means they could, in principle, be trained on machines that do not share a fast interconnect. The reason large model training requires a tightly coupled cluster rather than a pile of scattered machines is largely the communication pattern of end-to-end backpropagation. Break that dependency, and distributed training over commodity infrastructure becomes structurally more plausible. Nobody has demonstrated that at scale, and it is the implication I would most like to see someone chase. The DeepWeightFlow case is different and narrower. It does not lower the cost of the first network, it raises it by a factor of 100. What it lowers is the marginal cost of the 101st. So it democratizes access to populations of networks for tasks where somebody has already paid the corpus cost. That is genuinely valuable for research on ensembles, on weight space structure, on the variability of training outcomes. It does not put frontier training in reach of anyone who could not already do it. Both are real contributions. They help different people with different problems. Collapsing them into one narrative about the end of gradient descent obscures both. Let me develop the ensemble application because it is the one I think is most immediately real and it is underexplored in the paper. An ensemble is several models voting. It is one of the oldest and most reliable accuracy improvements in machine learning, and its benefit comes from deca-related errors. If your models are wrong about different things, averaging cancels some of the wrongness. The theoretical picture is that ensembling reduces variance without increasing bias, and empirically it also improves calibration. The confidence numbers become more honest, which matters enormously anywhere the output feeds a decision. The reason nobody ensembles as much as they should is cost. N models means N training runs. For anything expensive, that is the end of the discussion. Now, generate 100 networks in minutes from one corpus. The diversity measurement in the paper overlap of misclassified examples says the generated networks make genuinely different mistakes, which is precisely the property an ensemble needs. But I want to flag the experiment I would want before believing it fully, because diverse and diverse enough are different claims. Take 100 generated networks, ensemble them, and measure accuracy. Then take 100 independently trained networks, ensemble them, and measure. If the generated ensemble matches the trained ensemble, that is an enormous result. You have replicated the benefit of 100 training runs at the cost of one corpus plus seconds. If it falls short, the gap tells you exactly how much of the true training variability the flow captured, which is the cleanest possible measurement of the thing I have been circling for this whole act. The paper reports diversity metrics, but, as far as I can see, not that head-to-head ensemble comparison. It is a cheap experiment. It would be the single most informative number in the area, and I would like somebody to run it. Until then, my honest expectation, generated ensembles will help and will underperform true independent ensembles, because a 99-dimensional subspace fitted to 100 samples cannot contain the full variety of 100 fresh runs. But I would be pleased to be wrong. One consequence of weight generation that neither paper emphasizes, and I think will matter, possibly more than the training cost story, the generator never sees the data. I made that point earlier as a limitation. It cannot verify its outputs. But turn it around, and it is a capability. If you can train a flow model on a corpus of networks and distribute the flow model, then whoever receives it can produce working networks for the task without ever receiving the data those networks learned from. The training data stays where it was. What travels is a generative model over solutions that has obvious applications anywhere data cannot move: medical imaging across institutions, anything under data residency rules, any setting where the data set is the asset and the model is the product. And it raises the obvious question, which is whether the data can be recovered from the generated networks. The honest answer is that we do not know, and the literature on memorization and extraction from neural networks does not encourage confidence. Networks memorize training examples. If a generator produces networks that memorize, the memorized content has traveled, and it traveled inside something nobody was inspecting for it. I want to be careful not to overclaim in either direction. I have not seen work testing, extraction attacks against generated weights, and the fact that I have not seen it does not mean it does not exist. It is a question I would want answered before anyone deployed this as a privacy mechanism, and it is the kind of question that tends to get asked 2 years after deployment rather than before. So a real and under-discussed capability with a security question attached that, as far as I can tell, is open. I want to name the parts of this space I have not covered, partly for honesty and partly because one of them may be where the actual answer comes from. Zeroth order optimization. Estimate the gradient using only function evaluations. Perturb the parameters. See how the loss changes. Infer a direction. This needs no backward pass at all, and therefore no stored activations, which makes the memory story extraordinary. The problem is variance. The number of evaluations needed scales badly with dimension, and we are in 100 million dimensions. Recent work on memory-efficient zeroth order fine-tuning has made this practical in narrow settings, which is more than I would have predicted 5 years ago. Somebody in that thread guessed this was what the claim meant, and it was a reasonable guess. Evolutionary and population-based methods maintain a population, mutate, select. No gradients anywhere. These work. They are wildly sample inefficient for large networks, and they remain competitive in specific niches like reinforcement learning with sparse rewards, equilibrium propagation, target propagation, feedback alignment. The biologically motivated feedback alignment is the one I find most conceptually startling. It turns out you can propagate error backwards through fixed random weights instead of the true transposed weights, and the network learns to align with them. That should not work. It does, at least at moderate scale, and it is a real dent in the idea that backpropagation's exactness is essential. Learning in text rather than weights. Someone in that thread raised it, and it is a genuinely different frame. Keep the knowledge in a natural language artifact the model reads, rather than in parameters the model is. Whether that counts as replacing gradient descent or as sidestepping the question is itself an interesting argument. I did not cover these because they were not what the claim pointed at, and because 3 hours is already a lot. But if gradient descent is meaningfully displaced in the next decade, I would not be surprised if the mechanism came from one of those paragraphs rather than from either of our 2 papers. I have been skeptical for 2 acts, so let me do the thing that makes skepticism honest rather than reflexive. State precisely what would change my mind. If you see these, I was wrong, and I would like you to hold me to it. First, a weight generator that is trained on networks from task A and produces working networks for task B, where B was never in its training set. Not fine-tuning generation. That would break the bootstrap objection, because the generator would have learned something transferable about what trained networks are, rather than the shape of one specific cloud. The conditional generation experiments in the appendix gesture at this direction, they are early. Second, blockwise training demonstrated on a converted pre-trained model at a scale people actually care about. Take an existing open model, convert it, continue training blockwise, show parity. That removes the from scratch only limitation and the adoption path opens immediately. Third, a generated network that beats its teachers. Systematically, not by a fourth decimal place. That would mean the generative model had learned something about the structure of good solutions beyond imitation, and my ceiling argument would collapse. I do not expect this from the current objective, and that is exactly why it would be decisive. Fourth, any of this at a billion parameters plus, end-to-end, with the training cost of producing the corpus counted honestly in the comparison. That last clause is the important one. Amortization arguments are only meaningful when you include the setup cost, and papers in this area sometimes report generation time as if the 100 training runs were free. Fifth, evidence on the implicit bias question. Show me that sampled networks behave like descent-trained ones out of distribution, under distribution shift, under adversarial attack, or show me they do not. That would be just as interesting and arguably more useful. None of those are unreasonable. Several are plausibly 1 or 2 papers away. If 2 or 3 of them land in the next 18 months, the picture changes materially, and the person who said 6 months will have been directionally right and specifically wrong, which is the most common way of being right on the internet. Let me make some falsifiable predictions with dates, so this film can be checked rather than merely agreed with. Within 12 months, I expect blockwise or locally supervised training to appear in at least one mainstream training framework as an option, aimed at memory-constrained fine-tuning. The result is good enough, and the implementation burden is low enough. 3 modifications to a transformer that somebody will ship it. Within 12 months, I expect a DiffusionBlocks style method demonstrated on a converted pre-trained model rather than from scratch. That is the paper's own listed future direction, it is the obvious next step, and it is what makes the method adoptable. Within 24 months, I expect weight generation to be a normal tool for ensembling in domains where corpora exist, probably starting somewhere unglamorous like tabular models or small vision networks, where training 100 instances is genuinely cheap. I do not expect within 24 months a frontier language model trained without end-to-end backpropagation somewhere in the stack. I do not expect a weight generator producing usable billion parameter models for tasks it was not trained on, and I do not expect gradient descent to be absent from any serious training pipeline. If I am wrong about the last 3, I will have been wrong in the most interesting possible way, and the mechanism will almost certainly be something not covered in this film, which is a reason to take the roads not taken beat seriously rather than as a disclaimer. The prediction I am least confident about is the blockwise in a framework one, and not because the method is weak. Because adoption in this field is decided by whether something lands in the default path of a popular library, and that is a social process with almost no relationship to technical merit. Plenty of better ideas than this one are sitting unadopted in proceedings from 2019. So here is my honest position, stated plainly enough that you can disagree with it precisely. My honest position, gradient descent is not being replaced in 6 months. Gradient descent is being surrounded. Cheaper to run, cheaper to remember, occasionally skippable if someone already did it 100 times for you. That is less dramatic and much more likely to be in your stack by next year. Let me break that into the 3 mechanisms one last time, with a verdict on each. The optimizer. Actively evolving, genuinely competitive, and entirely within the descent paradigm. Muon and its relatives will keep taking ground. Nothing here is a replacement, and the people building them do not claim it is. Credit assignment, this is where I would put my money for near-term, real-world impact. DiffusionBlocks is a principal derivation of something people have wanted for 20 years. It works across 5 architectures, and its main limitation from scratch training only is the kind of limitation that gets removed by a follow-up paper rather than by a miracle. Memory is the binding constraint in this field. Anything that divides it by B and keeps parity is going to find users. The search paradigm, real, narrower than advertised, and pointed at a different problem than the one it is being sold as solving. Weight generation is not a training replacement. It is amortized ensembling and superior initialization, and both of those are worth having. The bootstrap requirement is not a temporary engineering gap, it is what the method is. And the meta point, which is the one I actually care about you leaving with, the interesting question was never, is gradient descent dead? It was, which of the 3 mechanisms is this touching, and what does the paper's own methods section say it needs in order to work? You can run that check in about 10 minutes on any announcement in this space, and it will be right far more often than the timeline in the tweet. Let me leave you with something more durable than my verdict on 2 papers, because 2 papers date fast and a method does not. When the next announcement arrives, and it will, this field produces 1 a month. Here is the sequence that takes 10 minutes and gets you most of the way to the truth. 1. Find the artifact, not the thread, not the summary, the paper, the code, the model card. If there is no artifact, you are done. There is nothing to evaluate. 2. Identify the mechanism. Does it change the update rule, the way credit reaches each layer, or whether you iterate at all? Almost every claim in training research is one of those 3, and knowing which one immediately tells you what could possibly follow from it. 3. Read the methods section for inputs. What does this thing need in order to run? DeepWeightFlow needs 100 trained networks, and the fact is in plain sight in the methods. That single question, what does it consume, catches most circularity. 4. Read the limitations. Section 6, the conclusion, the appendix, nobody links. Authors are usually honest here because reviewers make them be. This is where you learn that a method is from scratch only, or needs matching dimensions, or was not tried above 100 million parameters. 5. Check the comparison. Is it compared against a strong baseline doing the same job, or against a weak version of the alternative? DiffusionBlocks compares the converted network against the original trained end-to-end, which is the right comparison, and says explicitly why it only compares to forward-forward on classification. 6. Ask what would have to be true for the strong version of the claim, and whether the paper shows it. Usually it shows something adjacent and more modest, and usually that adjacent thing is genuinely good. That is it. Artifact, mechanism, inputs, limitations, comparison, gap, you can do it on your phone. There is a pattern in this film I want to make explicit before the boundary beat, because it is the most useful thing in it, and it is easy to miss among the numbers. Both of these papers work by finding a correspondence rather than inventing a mechanism. DiffusionBlocks did not invent a new way to train blocks independently. It noticed that residual networks are ODE solvers, that diffusion reverse processes are ODE solvers, and therefore that the training objective from one field could be imported into the other, bringing its independence property with it. 20 years of people handcrafting local objectives, and the answer was a correspondence to a field that already had the guarantee. DeepWeightFlow did not invent a way to model weight distributions. It noticed that flow matching, built for images, transfers to weight vectors if you first quotient out the symmetry that makes weight vectors incomparable, and the quotienting machinery already existed from a completely different line of work about merging models. Neither paper's core move is a new algorithm. Both are recognitions that 2 things people had been thinking about separately are the same thing. That is, I think, what most real progress in this field looks like, and it is nothing like the way it gets narrated. The narration is always a new invention arriving to overthrow the old one. The reality is, usually somebody noticing that a structure over here already has the property people over there have been trying to construct. It also suggests where to look next. Not at announcements of new mechanisms, at unexploited correspondences. What else is secretly an ODE? What other symmetry group is making a learning problem harder than it needs to be? Those questions have a much better hit rate than what is the next big thing, and you can ask them yourself. One last piece of context, and then the verdict, and then I will let you go. I do not think the people who post claims like this are frauds, and I want to resist the easy version of this film where I am clever and someone else is stupid. Here is what I think actually happens. A researcher reads something genuinely exciting. The excitement is real and often well-founded. Then they compress it for an audience, and compression is lossy in a specific direction. The conditions go first. Under these assumptions, at this scale, given this corpus, memory drops by a factor of b, becomes training is about to change forever. Because the second sentence fits in a post, and the first does not. And the incentive gradient, appropriately for this film, points downhill toward the compressed version. 71,000 views. The careful version gets 400. The papers underneath are usually fine. That is the thing I most want you to take away. Both of the papers in this film are careful, honest documents whose authors state their own limits clearly, including limits that make their own contributions look smaller. The distortion did not happen in the lab, it happened in the compression, which means The fix is not to distrust researchers, it is to go one layer down. The artifact is almost always more interesting than the claim about it, and it is usually right there free with a section 6 that tells you exactly what it cannot do. So gradient descent is not dying in 6 months. It is being made cheaper to run and occasionally skippable if someone already ran it 100 times by 2 good papers that both say what they need in order to work. And tung sahur can in fact be trained into godhood. It takes 100 epochs, a cosine schedule, and someone willing to do it 100 times so a flow model can watch. There is no shortcut to the first one. There never is. Let me be concrete about how a training method actually reaches you, because it is not by being good. A method reaches practitioners when it lands in the default path of a library they already use. That is essentially the whole mechanism. Mixed precision training became universal not when the papers appeared, but when it became a flag. Gradient checkpointing became normal when it became a function call. Flash attention became ubiquitous when it became the default attention implementation. So the question for DiffusionBlocks is not whether it works, the paper establishes that, but whether the 3 modifications can be wrapped in something that takes one line. Partition, assign noise ranges, add conditioning. That is a transformation over a model definition, and it is exactly the kind of thing that can be a wrapper. If somebody writes that wrapper and it lands in a popular training library, adoption could be quick. The obstacle is the from-scratch limitation. Most people fine-tune, comparatively few pre-train. A memory optimization that only applies when training from scratch addresses the smaller population, which is why the paper's own listed future direction, converting pre-trained models by fine-tuning, is the load-bearing one for adoption, more than any scaling result. For weight generation, the adoption path is different and narrower because it needs a corpus, and corpora are not a thing most teams have. My guess is it arrives first as infrastructure inside organizations that already train many small models as an ensembling service or an initialization service, rather than as something an individual practitioner installs. And both will be described, when they arrive, as gradient descent having been replaced. It will not have been. It will be sitting underneath in every block and in every one of the 100 runs that built the corpus. Let me close the running argument because it has been carrying real weight and it deserves a proper ending. Tung sahur can be trained into godhood. He can also apparently be sampled into approximate godhood in about 4 seconds at 93.5% godhood, provided 100 people achieved real godhood first and let a flow model watch. That is not a joke about a meme. That is a precise summary of the technical situation, and I would like to defend it as such. Godhood, in this metaphor, is the trained state, the setting of the weights where the network does the thing, and the pilgrimage is gradient descent, 100,000 small steps, each informed only by the local slope, in a space no one can see. DiffusionBlocks does not skip the pilgrimage. It lets each stage of the route be walked independently, so no single pilgrim has to carry the whole journey in their head at once. That is a logistics revolution, not a theological one. DeepWeightFlow watches 100 completed pilgrimages and learns the shape of where people arrive. Then it can drop you there, 93.55% of the way there in seconds without walking. But it learned that destination from the walkers, and if nobody has ever walked to a particular destination, it has nothing to show you. I have received a second holy vision from the gradient descent gods, and it simply said, the vibes are directionally correct, but the timeline is cope, which I think is the fairest possible summary. Something real is happening. Training is getting cheaper in ways that will change who can do it. Weight generation is a genuinely new capability with genuinely useful applications. And the specific sentence, gradient descent dead, 6 months, bigger than transformers, is not supported by either of the papers it was probably pointing at, and both of those papers say so themselves in their own conclusions in plain English where anyone could have read them. A closing thought about how this field talks about itself, and then I will stop editorializing. There is a genuine tension between two good things. Research needs enthusiasm. People work on hard problems for years because they believe something big is possible, and that belief is not a bug. And communication needs compression. Nobody can read every paper, so somebody has to say what matters. The failure mode is when compression happens without the conditions traveling alongside. Memory drops by a factor of b when you partition a residual network into b blocks and train each on its assigned noise range. At parity from scratch on models up to this size compresses to training just changed forever, and the compressed form is not false exactly, it is unfalsifiable, which is worse. What I would like more of is not skepticism. Skepticism is cheap and mostly performative. What I would like is the habit of naming the conditions when you are excited. This is great, and it needs a corpus of 100 trained networks, is a sentence that is both enthusiastic and honest, and it takes 4 extra words. Both papers in this film do exactly that in their own conclusions. The Sakana group says they do not understand their own block count result. The Northeastern group says their canonicalization stops helping at moderate dimension. Neither had to. Both did. So if you take one thing from 3 hours, the artifact is almost always better than the discourse about it. Not more exciting, better. More surprising, more specific, more useful, and more honest about what it does not know. And it is free, and it has Section 6. Let me separate what this film demonstrated from what it asserted, because those are different categories, and the difference is the only thing that makes 3 hours of this worth anything. Demonstrated, in the sense that you can go and check it yourself from the papers. The memory cost of end-to-end backpropagation scales with depth, because activations must be retained for the backward pass. DiffusionBlocks reduces that to roughly 1 over b by giving each block an independently optimizable objective derived from denoising score matching, and reports parity across 5 architectures in 3 domains with 4 times memory reduction on autoregressive text. Applied to a recurrent depth model, it replaces 32 iteration training with a single forward pass. DeepWeightFlow learns a flow in weight space and generates complete networks that reach 93.55% on cipher 10 against 94.45 for the networks it learned from in seconds rather than hours, and those generated networks transfer to new datasets far better than random initialization. Its training set is 100 conventionally trained networks per task. Every one of those is checkable. The locators are on screen and in the description. Asserted by me, and therefore yours to reject, that these are best understood as changes to 2 different mechanisms, credit assignment and the search paradigm, rather than as one thing called replacing gradient descent, that the bootstrap requirement is structural rather than a temporary gap, that the honest framing of weight generation is amortized ensembling and initialization rather than training replacement, and that the distinction between changing what models can do and changing what training costs is the distinction the original claim elided. Those are arguments. I have tried to give you the evidence to argue back, including the parts that cut against me: the 4th decimal place win on BERT, the conditional generation appendix, the possibility that optimizer choice affects which minima you find, and therefore that my clean 3-way split is too clean. Now the limits, and there are more of them than usual because this is a live area moving quickly. We did not run anything, not one experiment in this film was performed by me. There is no GPU here, no cluster, and no reproduction. Every number came from a paper and is attributed to that paper, with a locator. Where I quoted a vendor or an author's own performance claim, I said whose claim it was rather than adopting it. If either paper's numbers are wrong, this film is wrong in exactly the same places, and I have no independent basis to catch that. We did not cover the whole field. 0th order optimization, estimating gradients from function evaluations alone, is a real line of work, and it is absent here. Evolutionary and population-based methods are absent. Equilibrium propagation, target propagation, feedback alignment, and the broader biologically plausible learning literature got a sentence each at most. Learning in text rather than weights, which somebody raised in that same thread, is a genuinely different idea and is not covered. Any of those could matter, and none of them is what the original claim appeared to point at. We did not resolve the implicit bias question because, as far as I can tell, nobody has. Whether a sampled network behaves like a descent-trained one under distribution shift is open, and I flagged it twice rather than answering it. We did not read the open review discussion. DeepWeightFlow is an accepted ICLR 2026 paper, and its review thread is behind a check I did not attempt to work around, so I used the archive version, which is the same paper. If the reviewers raise something material, I do not know about it, and the specs will date fast. This is a field where 6 months genuinely does change things, just not always the thing that was promised. If you are watching this a year from now, treat every not yet demonstrated at scale in this film as a question rather than a fact. and go and check. One last thing, and then I will stop. The claim that started this was a single sentence with no numbers, no scope, and no conditions under which it would be false. It got 71,000 views. The papers underneath it contain careful derivations, honest limitation sections, and at least one result where the authors undercut their own headline method because that is what the data said. I do not think the person who wrote that sentence was acting in bad faith. I think he was compressing something real, that a lot of interesting work is happening on how training works, and that some of it is unusually promising into the form that travels. And the form that travels has no room for the conditions, and the conditions are where all the meaning is. The useful skill is not detecting hype. Detecting hype is easy and mostly makes you tiresome. The useful skill is the one I have tried to demonstrate for 3 hours. Take the exciting sentence, find the actual artifact underneath it, work out which mechanism it touches, and then read what its own authors said it needs in order to work. That last step is where almost all the answers are, and almost nobody takes it, because it is in section 6, and section 6 is boring. Gradient descent is 100,000 small steps taken by something that cannot see, guided by nothing but the slope directly underfoot. It has survived every architectural revolution of the last 40 years, and it is currently being made cheaper from 2 directions at once by people who are careful about what they claim. That is a better story than it dying. It is also the one that is true. Everything in this film is sourced. The papers are linked below. Go and read section 6.